2019. وفيما يلي سنتعرف على أبرز المشاركين في هذه الجلسة.
Ladies and gentlemen, welcome to the fourth session titled Renewables and Emerging Technologies for Evolving Energy, chaired by Asim Uthman Al-Qadi, Head of Technical Development, REPDO, Ministry of Energy. First paper, Optimal Designing of Solar Power Electric Vehicle Charging Station, presented by Muhammad Alam, Aliqra Muslim University. Second paper, Placement of Electric Vehicle Charging Station in Metropolitan Areas using an Agent-Based Network Graph Method, presented by Ahmed Abdul Azim, Furnas Showman. Third paper, a multi-vendor digital substation, concept, design, and implementation, presented by Dr. Fred Steinhauser, Omicron. Fourth paper, Smart Control and Monitoring of Industrial Power Systems using a Power Management System, presented by Michael Borky, Saudi Aramco. Fifth paper, Power System Studies for Wind Farm Interconnections in GCC, presented by Yergo Varhigi, Siemens. Sixth paper, Impact of Renewables on the Kingdom's Utility Fuel Mix, presented by Muhammad Nassar, Saudi Aramco. Seventh paper, Techno-Economic Feasibility Study of Supplying Existing Saudi Aramco Facility by Photovoltaic Farm, presented by Badr Al-Ataibi, Saudi Aramco.
جلسة حافلة. رحبوا معي بمدير هذه الجلسة الأستاذ المهندس عاصم القاضي وجميع المشاركين فيها. أهلا وسهلا بكم.
Thank you very much. It gives me a true pleasure welcoming you all here in this session 4. This conference is becoming a platform of a unique experience and topics in the field of a smart grid and the integration of new technologies to the grid. The belief of many organizations and sponsors made this event successful in bringing all the professionals around the region to share experience and connect. In this session 4, we aim to share a very interesting topic that has been prepared with very selected speakers that are going to share valuable topics to you and share experience. So, my name is Asim Al-Qadi, and I'm delightful to chair this session. And with no further introduction, we have the selected 7 speakers that are going to share valuable topics with you. And we are going to start with Dr. Muhammad Alim. Dr. Muhammad has worked in Chrysler and Ford Motors Company in the research and development in Michigan and US until 2015. Dr. Muhammad, he's the director of the Center of Advanced Research in Electrified Transportation and also a visiting research professor at Illinois Institute of Technologies in Chicago, US. He's well known on authorization and being authorized and co-authorized of more than 150 publications. So, ladies and gentlemen, please assist me in welcoming Dr. Muhammad to the stage.
It's not on. Bismillah ar-Rahman ar-Rahim. So the title of my presentation is Optimal Designing of Solar-Powered Electric Vehicle Charging Station. So the authors are Mr. Samir Al-Sharif from Taiba University, myself, my student Furqan Ahmed, and Dr. Ibrahim Saad Al-Saidan from Qasim University. This is basically we have developed a hardware. It's the first solar charging station in the country. Just to give you the background before I go to the presentation, the electric vehicle deployment started in India in 2015 April with a mission called FAME, Faster Adoptability and Manufacturing of Electric Vehicle, by Ministry of Heavy Industry, Ministry of Science and Technology, and Ministry of Road and Transport. So I'm one of the advisors to the Government of India, and we have taken about a grant of $1 million, and we have established this Center of Excellence for Charging Infrastructure. It's called CARET in Aligarh Muslim University. So we have developed different charging stations for two-wheelers, four-wheelers, fast charging stations, this particular solar power charging stations. And then right now we are developing a solar-powered wireless charging station. We have also developed blockchain, IoT-based management, advanced cloud management, and big data management for charging stations. So starting my presentation, how to go to next slide. It's not going.
This was forward, this one backward.
So the motivation, as we know, and you might have seen in the news, the level of pollution in the country, that it's as much polluted Delhi is right now, like you are smoking 36 cigarettes a day. That much pollution in Delhi, and it happens in the month of February and November, when they have those festivals where they either burn the firecrackers or they burn the trash. At that time, and then the number of vehicles in every urban population, it's the same case. So that needs to address. The government is trying to address through different ways. They have allocated this FAME mission. And right now there is a need, and it's becoming an egg and chicken issue, that if we have the electric vehicle, how we are going to charge them. But if we are going to charge them, we are the electric vehicles. So the objective for this particular station was that we can develop a level 2 solar power charging station that can charge the electric vehicles and promote a standardized and economic system. And it is very convenient. Every parking station, they can have the solar powers that can provide the charging while the vehicles are parked. And when vehicles are not parked, then this solar parking will provide the power to the building or to the office where they are located. So the concept of solar power charging station is nothing new. It's an old concept. It's been in the world around for last 10 years. But what we have done is there are 3 levels of charging stations. The level 1, which is 110 volts, which concept is that you bring it to home, you charge it overnight, and then you drive to work next day. The level 2 charging station is 220 volts, and it meant to that when you are at the workplace, or you are at your university, or you are there from 9 to 5, during that time, during 4 to 6 hours, it can be charged, and it has to be paid through credit card or through your online account. And then we have the level 3 charging, which is also called fast charging. The first standard developed by Japan, and cha demo. That words come from the Japanese word cha demo. Let's have a cup of tea, cha demo. So while you are having a cup of tea, the vehicle will be charged within 20 to 30 minutes. But that fast charging, it at the cost of the health of the battery. So you are deteriorating the state of the health of the battery. So here we have took a medium path, and we have chosen the level 2 solar charging, where the people can come, they park their cars, as you have seen all over in Saudi Arabia also, that you have canopies, where you park your cars in the parking. So instead of those canopies, you can have the solar panels. So while your car is parked over there, your car is being charged. On holidays or at the time the sun is out but the car is not parked, then the same solar panels will provide the clean, green and renewable power to the adjacent building, and it can be part of the local smart microgrid as well. The contribution we have designed from the concept all the way to the hardware implementation, and right now we are collecting the data for last 1 year, and we have developed the unique power conditioning unit that address the power quality aspects, both at the vehicle side, and also we are feeding it to the local grid, so the power quality aspects over there we have also addressed over there. And then we have done the detailed cost analysis for a commercial viability perspective. So this is the outline or the layout, the way we have the solar charging station over there. We have solar power arrays. So we have 6.6 kilowatt solar panels over there. Then we have developed this combiner box, and then we have charge controllers. Right now we are using a simple charge controller, but we are working on introducing the fuzzy logic and the AI based controller as well. And I can monitor the input and output of the solar power, how much is going into the vehicles and how much I am feeding into the grid. Or on a cloudy day to charge a vehicle, I am taking it from the grid. It's a cloud base and I can look at my phone as well. And the general level 2 charging station that we have electric vehicle supply equipment. And then for testing purpose, we are using J1772 connector, but very soon we are going to switch over to the connector which are going to standardized by the government of India. And then on the vehicle, we have onboard charger, and then we have vehicle battery pack. So we are using lithium-ion battery pack. And then we are using the test vehicle is Mahindra E2O, which is 2019 model. And it has 3 different types of batteries that we are testing over there. So we have taken, as I said, 6.4 kilowatt solar panels. And Aligarh Muslim University is the one of the government university. It has about 30,000 students. It's more than 100 years old university. Is located about 2 hours from Delhi. And it has extreme hot and extreme cold weather. And this system compromise, we have put the 20 panels, 2 in series and 10 in parallel. So total we are getting about 320 watts every solar panel. And it can supply up to 6 kilowatt charging per day. So we are able to charge 2 4-wheelers and 2 scooters, 2 electric scooters. So we have electric scooters from Hero Eco Company, and then we have this Mahindra E2O. And then in-house we have developed an electric vehicle. We have retrofitted a gasoline vehicle to a electric vehicle. So these 3-4 vehicles we are charging over there. This is just to give the institution load profile. The time when we are not using the vehicle for charging, at that time we are able to provide the center building, which has I've given the detail. We have fans, tube lights, CFLs, and computers. So we are able to power the whole building through this 6.6 kilowatt charging station. So except the air condition and heating, all the basic load is being sourced by these solar panels. And this is the pictorial view of the charging station. So these are the there. And then we are able to charge 2 4-wheelers. On the left, yellow one is the electric rickshaw, which if you go to India, you will find it very common mode of transportation right now. On the right side is the 2-wheeler. Then a challenge was to design the controller battery charger circuit, which we used as the DC to DC converter and also DC to AC inverter, which 50 hertz and 240 volt output. And we have used the PWM pulse width modulated boost rectifier and bidirectional DC to DC buck converter, which can produce about 48 volt DC input. And this is the converter topology that we use. So we can charge the vehicle. We can also provide the power to the building. The building can provide the power to the system to charge the vehicles. And on top of that, recently we have introduced the vehicle to grid as well, that through the bidirectional DC to DC converter, if the vehicles are fully charged and if there is a peak demand, we are able to feed into the local grid from the vehicle as well. So it's V to G, G to V, V to H, and H to V. Both 4 aspects we have integrated into the topology. And these are different modes of working. Mode 1, Mode 2, Mode 3, and Mode 4. So Mode 1 is when we are charging the vehicle. Mode 2, when we are providing the power to the building. Mode 3, when the building is providing the power to charge the vehicle when there is a cloudy day or sun is not available. And Mode 4, when the vehicles are fully charged and there is a peak demand and we are providing power to the grid. And these are different results of charging circuit. If you can look at it, that we have a very smooth voltages output and also the current that we are required over there. So through this power conditioning unit, we were able to address different power quality issues, especially the total harmonic distortion and the voltage sags. That was one of the earliest issues that we were facing. So we were able to obtain a smooth voltage and current profile. And there's also the bus voltage, and we have the input and voltage of the H-bridge inverter. So we can look at it, a smooth uniform profile is there, and that is very important for the lithium-ion batteries that we are using. If we provide the voltage surges that are going to hurt the battery life, and in fact the BMS and the BTMS, battery management system and battery thermal management system as well. This is the hardware setup. So firstly, we have developed in the lab. This one we have developed in the lab. After we have tested it in hardware in the loop through NI system and through OpenRT, then after that we have integrated into the system over here. So this is the box that we have made. It has batteries on the bottom, and then we have fans inside there to cool the system. And then you can monitor from this screen also the current status of the batteries, and also how many vehicles they are being charged. And another TV panel is inside the building where you can monitor it, and I have on my phone also where I can look at it. So this is the hardware in the loop EV charging profile that we have tested before we have installed it. So developed the model, tested it in the hardware in the loop on the bench, and then we have installed it in the hardware. So this is I have a short time, so I'm just skipping few things. These are the experimental results. So you can look at it over here, that we have this figure demonstrates the experimental waveform which we form out in the booster charge. And this figure represents how the AC to DC rectification stage respond to the variation in the load. So for this particular situation, we have used a compensator feed forward, which is additionally executed in the controller algorithm. Further, the bus, we found out about 325 voltage. This shows the output current and the output voltage waveforms for the electric vehicle charging station, and also the load dynamics, which manages the DC inductor current, which is constant throughout the controller.
Okay. 2 minutes.
And as you can look over it, here is the profile that how much we were able to take in the charging from the solar, how much we have given it to grid, how much we have taken it from the grid, and how much we have given it to the energy storage in the in-house. So as you can look at it, during the winter time, we were taking the power from the grid. During the summer time, we were taking from the solar. And at certain times, we were able to store the energy as well. So I will skip those slides. These are comparison of different sites. So from this particular charging station, we were able to also have a startup. So this Center of Advanced Research in Electrified Transportation, CARET, has recently been awarded by the Government of India as the Smart Incubator of the Year. So we have incubated 5 startups. So one of the startups, SS Indo Solar, is now commercializing the solar charging station in the country. Any question? Thank you very much.
Thank you very much, Dr. Muhammad. It was very well developed technical papers, and it came to my mind, all these studies, where have been developed, where, of course, there is a well-developed facilities in developing these chargers and developing all these experiments. If you can give us more elaboration on that. Sorry, I can repeat the question. So we want to know from all these experiments and the lab, where have been conducted at? It has been chose that it will develop, let's say, experiments.
So as I said, in 2015, this FAME mission has started, and they have given us a grant to Aligarh Muslim University for about 7-8 crores, which is almost $1 million. And then we have developed the Center of Excellence for Charging Infrastructure right in Aligarh Muslim University in India. So first we have developed 5 labs. So we have a smart charging lab, we have a smart microgrid lab, and we have a hardware in the loop lab, intelligent transportation lab, and EV workshop. So all the, actually we have 12 patents also on these charging stations. So first we have developed the models, and then we have developed the hardware in the loop system, and then we have developed the prototypes. And based on those prototypes, we have developed the hardwares. And every single charging station hardware, we are testing it. We have a collaboration with one of the automotive industry in India. For example, for a two-wheeler charger, we have collaboration with Hero Eco. For solar charging station, we are testing it on the Mahindra E2O. So every single commercial vehicle which is on the road, we have tested these charging stations for their viability.
Very well, and thank you very much. So we can allow maybe for one questions from the audience, please. If someone can help us in moving around with some microphones. Please, some of the technical team can help us and provide the microphone.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, Doctor, for your presentation. You say that the sun shine for 6 to 8 hours, so the photovoltaic system can charge the battery storage. You didn't say what is the rating of energy storage system. And what about study of economical or economical study? Thank you.
The payback period is about 1.5 years. In 2 summer seasons, we were able to get the investment that we have done for the solar panels and the whole charging station. So that was the economic analysis. We have 10 solar panels, one is 320 watt each, so it's about 6.4 kilowatt, and whatever it cost, including the labor and the deployment and the circuits, so 17 to 18 months is the payback period for the whole deployment.
Thank you very much. And here we conclude our first paper. So now we're going to move with the second speaker, with Engineer Ahmed Abdelazim. Ahmed is an engineer and researcher with more than 12 years of professional experience in infrastructure, renewable energy, and energy efficiency sectors. He holds a master degree in energy utilization and bachelor in electrical engineering. Ahmed has provided consulting services for more than 1.6 gigawatt of solar PV plant, as well 200 megawatt of wind power plants. Ahmed, please, you are welcome to the stage.
Good morning. My name is Ahmed Abdelazim. To complement Dr. Alam's presentation, I will be speaking about the placement of electric vehicle charging stations, especially in metropolitan areas, which are areas within a large city. As you know, the transportation sector consumes about 19% of the world total energy use. This is according to the International Energy Outlook. Fossil fuels, of course, produce emissions from greenhouse gases, and the 19%, of course, contribute significantly to this kind of emissions. The promotion of cleaner transport technologies has been one of the pillars of sustainable development. Because it contributes to the 7th goal of the UN, which is affordable and clean energy. As this chart says, you can see that the main markets that lead the world in this transformation is China and Norway. The motivation for this research is EV is growing. The electric vehicle usage is growing, and the prices are continuously dropping, mainly because of the cost of the energy storage, because mainly the electric vehicle is about battery storage. So when battery storage when the technology of battery storage is advancing, the prices are dropping naturally, and consequently the price of EV is dropping, which promotes more and more adoption by the end user. According to studies, the main issue that impedes or resists this kind of proliferation of electric vehicles is what we call the range anxiety, which is the fear of the person using the EV or considering the use of EV cars that the battery will run out while he's on the road. So the main issue, consequently, is how to establish an infrastructure for charging the cars, a public infrastructure for charging the cars, similar to the fuel stations that we are all accustomed to. The policies are, of course, the policies of the national policies, of course, are supporting the deployment, but naturally they're not enough to accelerate the adoption of the electric vehicles, mainly because of the infrastructure is usually costly. These are the kinds of, I've listed just the kinds of investment costs that are usually borne by the national budgets if the country chooses to adopt electric vehicle charging infrastructure, like the equipment installation itself, the operation maintenance, the cost of energy itself, and the legal, of course, and licensing fees. Therefore, the private sector will step in and try to fill the gap that national budgets and governmental efforts and public efforts in general are lacking. And as we know, the investors in the private sector are mainly looking for profit, and therefore they're looking to maximize the coverage of any infrastructure that they would be investing in, while minimizing their capital cost or what they pay for it. Therefore, the infrastructure has to be optimized, whether the locations, the number of units of charging, and this all related costs should be optimized so that the coverage is maximized and the profitability is enticing for the private sector to step in. The main problem of deployment of electric vehicle charging infrastructure is broken down into three main components: the placement of the charging stations itself, where should I put the stations, and the power supply, how should I power the charging stations? Should it be from the grid? Should it be from PV technologies like Dr. Alam's suggestion? And queuing, of course, how many units in the charging station to avoid congestion, if any, to collect the return on investment on the station in a profitable way for the investor. In this research, we're targeting the placement problem of the EV charging stations. So this is the main questions that we're targeting. Where should we place public charging stations so that it optimally serves a large metropolitan area, a large city? I'm from Cairo, so this has been applied to Cairo, but of course it can be applied to any large metropolitan area. For the methodology, most researchers have or can be categorized into two main categories. The agent-based modeling, which in summary models the behavior of the users of the EV, and graph theory, which tries to model the road network of the city, of the road network of the region that I'm trying to study. In my research, we combined both approach into a hybrid approach, which both simulates the behavior of the users of the electric vehicle and simulates or represents, let's say, the road network of the city that we're targeting, so that we can study where exactly in the city should we place the stations in order to better serve the whole of the city. I used Python. Like we said, the model consists of two parts: the model for the network of the roads of the city, which in our case is Greater Cairo, and the drivers themselves as agents. We call it, in programming language and in modeling language, they're called agents, who are models of real persons, but which tries to capture their behavior and the motivation for their actions. First, we'll talk about the road network graph. We used graph theory, which divides the city into a set of nodes and a set of links between the nodes. The nodes, of course, are, we can think of them as the intersection of roads, and the links between the intersections are, of course, the roads. For the case of this study, we included 8 edge cities, which are cities in the greater Cairo area, and mostly new cities, but which are currently being frequented by Cairo commuters, whether to go to work or to live, to go back home. These, of course, this simply the distance between the respective city and downtown Cairo. On the other hand, the driver agents, they are implemented as, like I said, like programmatic objects, classes, and they have sort of like a list of behaviors or properties that include, for example, the home where he lives, the destination where his trip is going to, the current location while he's driving, the charge level of his car, the anxiety level, the range that the car can cover, and some other, I can see, as you can see, some other attributes that are trying to capture the behavior and the motivation for action of the agents. The general steps for the simulation approach is that we instantiate, create a large number of EV drivers within the network, and let the agents drive through the network, and then we register the places where they run out of charges, because like I said, they're random and their charge state is random, so some will run out of charges before reaching their destination, some will not, some will reach the destination, some will not. The locations are registered, and then we count the location, we survey the location, we perform a frequency analysis on the locations, and like it's being stated here is that the rationale of this is that the more EVs run out of charge in a specific area, we can conclude that this area needs an electric charging so that he can charge his vehicle while to continue his trip. This is the network of Cairo that we have developed. If you look closely, you'll find that most of the edge cities are included, and the center of Cairo is the central area, of course. These are the assumptions in the model that we've used. Of course, all models are simplification of reality. So these are the assumptions. We have assumed that the average user uses a compact city car, which something like the Spark, for example, or this kind, which are commercially available. The mileage of electric vehicles is assumed to be 6 kilometers per kilowatt hour. This is obtained from the EPE data. The routing through the network is done mainly through the distance. It's distance based, so there's no time consideration. Sometimes, of course, the shortest road it takes more time because of traffic, but this is, of course, ignored in this research. The driver agent can start the trip from any location on the network, including
Ahmed, you got 2 minutes.
Okay, I'll just run through this. I'll go to the resultant discussion. Like I said, this is the modeled network. I've treated 5,000 agents representing people who are using the electric vehicles. And like we said, we collect the locations where they run out of charge within the network to conclude the places of placing the charging stations. And these are the links where the links are roads, of course. The links where the algorithm recommends placing the electric vehicles, the charging stations of the electric vehicles. Of course, if you look closely, you'll find that we have covered 53 or more than 53% of the whole city with merely 10 stations, which is a very good optimization. Like in this conclusion, we say that we have optimized, we have chosen 10 out of 53 possible locations, covering more than 50% of the city, which is a very good optimization. For the future work, of course, I propose to study the sensitivity of the proposed model to the assumptions, the effect of road traffic congestion of the placement algorithm. Like I said, we ignored any time constraint, the queuing problem at each station, and the placement of charging points based on some map of distributed energy generation sources like rooftop PV systems, for example. Thank you. Any questions, I'm open to.
Thank you. Thank you very much. So I saw the studies, and I'm wondering is that most of the study has been conducted in Cairo between the 10th of Ramadan city and October and Badr city. So is that has been advantage to you to build the studies and the research of your experiment?
You mean in the city?
Yes.
Yes, the motivation mainly is about developing something that can be used by, like I said in the presentation, by the investor to optimize his investment in electric vehicle charging infrastructure, because like I said, the private sector is supposed to step in to fill the gap of public funding of this area, the area of infrastructure in general, and of course of new technology like electric vehicles. So the main target is large cities first, and then of course by priority, and then we can move to any larger regions or other regions. Yeah.
Thank you very much. So we may allow for one question from the audience, if there is an interest to raise one. All right, so we will move to the next speaker. So our next speaker is Engineer Fred Steinhauser. Fred studies electrical engineering at the Vienna University of Technologies. In 1998, he joined the Microelectronics, and since 2001, he focused on so many standards with the International Electrotechnical Commission, with the digital substation, and being active with SIGRI. So please, Fred, you are welcome to the stage.
Can I use this microphone? Yeah, thank you, Mr. Chairman, for the introduction. Ladies and gentlemen, I have the pleasure to talk to you about the evolving topic of digital substations, and I do that also on behalf of my co-authors, Priyanka Mohapatra, who is the Senior Project Manager at Scottish Power for this project, and my colleague Matthias Wechinger, who had the greatest share in developing and conducting the testing procedures in this project. This project I'm talking about has the catchy name Fitness. You see here how this acronym was derived, and it is a kind of a milestone in a bigger achievement, how to optimize how Scottish Power will run their electrical system in the future. This is under this RIIO initiative, I'm not going into this here. It is very well documented. You can find materials about that on the internet, and I just have provided 2 links here in this slide. Now, what is this project about? It is about turning something like on the upper picture with a lot of copper buried in the ground to wire up the primary equipment to the protection, automation, and control equipment into something that is just using digital links, network connections to bring this information over and getting all the benefits from this kind of technology. There were some objectives defined for this project. You see this here lined up. I won't read it, all of them, but it has the goal to go with 61850 technology and also prove that this can be done interoperable with a multi-vendor installation, so that the whole thing does not need to come from one hand only, that this is really possible to go for this promise that 61850 has made. Different connectivity options means look into different architectures which are theoretically possible and try it out. Reducing of copper wiring, I just mentioned that on the slide before, and this topic will come again. And safety, you see here, safety is coming up also in this considerations repeatedly, a point which has to be regarded more and more in the future. The benefits which were also listed by the project owner are on this slide, again starting with saving the copper wiring, but we see here also the interoperability aspect, which is very important, and testing options during operation. So this is not only about setting up the station and being happy to have it commissioned. It's also thinking beyond that to say, how will we do with this when we are in operation? How will the maintenance personnel go with that in the future? And again, the benefits from safety are here. This has much to do with the non-conventional instrument transformers. From the way they are built, how they physically work, there is a potential that we get gains in safety from that. Back to the easiest to understand argument in terms of economical savings, that's the saving of copper wiring. You see here on the left picture how much of an effort it is to do this wiring right. And on the right side, you see a snippet from a paper which was presented last year, and this paper is a case study on its own, how 1.5 layers of copper wire bundles in a cable trench can be converted to a couple of optical fibers in a 10-centimeter tube. And I think this alone is something which is quite impressive. Now, who are the players in the rest of this presentation? Of course, there are many more players in this project, but I will focus now on the protection, automation, and control aspect in this station. There is, first of all, Scottish Power Energy Networks, the owner of the project, the owner of the substation, which was equipped with this digital substation technology. And then there are General Electric and ABB. There were 2 main vendors who were awarded with equipping the substation, and we will come back to that. And from the beginning, also Scottish Power wanted to have somebody in the boat who can give input and provide some knowledge about testing digital substations, and this is how the company I work for came into this game. Here you see an overview of the architecture in this Wishaw substation where this project was implemented. Don't try to read the picture, it's too detailed as always, but what you can roughly see, it's about 2 feeders with 275 kV lines. And now we go into these 2 feeders. The first feeder was under the lead of General Electric. You see, they provided the main protection. They decided to use the HSR architecture as a redundancy architecture for the network. There are merging units with non-conventional instrument transformers. These are from GE as well, but there are also merging units from ABB for the conventional CTs and VTs. And here there is already forced interoperability by design. This is not only clean made from one vendor, they already had to cope with each other's devices to prove that this works. And the second feeder is more or less a mirror image of the first feeder. This feeder was given to ABB. They led this implementation. They provided the main protection for that. They went for a PRP architecture to cover the redundancy. There are, again, merging units with non-conventional instrument transformers and a merging unit from the other manufacturer, from GE, for the conventional CTs and VTs. Again, forced interoperability. And we can say they both made it work. It can be done, and now these results are available to choose from for the next business as usual deployment in the future projects. When it comes to 61850 substations, we always have to think about the engineering. And there it is very advisable not only to think about the implementation stage, let's say FAT, commissioning, and that's it, because you can take some shortcuts when you limit yourself to that. You should always take the whole life cycle of the substation into consideration, look at the engineering already in the design stage, work it out very well and detailed during the implementation, so you have a very well-documented system. And it was already mentioned, the ongoing work with maintaining and operating the system was in the consideration, and such a well-done engineering is very helpful afterwards when somebody has to maintain the system, somebody who has not been involved in developing and commissioning the system, because he will find a lot of information in that when he has good engineering data available. So not allowed to take shortcuts in this regard. Then know your system. When you set it up, be sure that there are no white patches on the map. And how do you know your system? You're going to measure and you're going to test. And there is much to test. Only a couple of points are here on this slide. It starts with the time synchronization. This is very important in digital substations because all the data acquisition has to be neatly time-aligned to have the option to perfectly calculate with data which are acquired. Then network latency is something you have to look into. This performance of the network has to be verified to see if we can be as fast as we want it. And then, of course, we should have a look into the network load. Do we have any bottlenecks there? How can we resolve that? And you see, the first 3 points on this slide are all over the network. So commissioning the network first to ensure that there is the backbone of the system where we can build our protection application and control on top of that. This is really key now in digital substations. It's not just a side topic. When we have done that, we can go into that what we always did, protection testing, to see if we can control the system in fault conditions, and also go into investigating the behavior against the SCADA system. Lots of testing to do, and there was really an effort done in this project. Also, for later on, when you're in operation of the substation, you cannot go on without isolating the scope of testing. You need to do that in a way that you do not affect the rest of the system, which is still in operation. This has to be done via new measures which are provided in the standard, and at the time when this was implemented, the whole thing was just mature enough to be applied. This has also been proven that this will work. Here is a picture from the FIT where these efforts have been undertaken. The system had been pre-assembled, brought on site, connected to the primary system.
You've got 2 minutes.
Thank you. You see, there are some checks to be done, like here the guys checking the instrument transformer connection, if it fits with the expected polarity and so on. But by doing these pre-checks in the FAT, the on-site work could be reduced very much. You can now commission such a system within days and not within weeks. That's really an achievement of the good preparation. Now, gathering the experiences and keeping it on its own is not maybe the best thing. There were experiences shared with other people interested in this topic. Here's a picture from people from Statnet coming to visit already during the FAT. They made such a project on their own, which is another case study. Here, Vattenfall visiting the system, learning from it, and the Packwald conference made an excursion to the substation. So these topics are well documented. There are a lot of papers out of it, and I can only recommend for everybody interested in this, go after these materials, share the knowledge. These people are also open if you approach them to talk with you about that. You do not need to make every experience on your own. There is already best practice out there. So to conclude, there are many ways to implement a digital substation. Some of them were tried out in this project. All of them work. You can choose from it. I'm curious which one will be chosen. Scottish Power for the future rollout. Multi-vendor interoperability is possible to do. Testing is key. Make sure that you find out very soon what's going on, then you can easily fix it. And sharing experiences will lead to best practice. And having said that, I thank you for your attention.
Thank you very much. It got to my interest that we saw the digital substation. It has less couples, wiring, less space, and more. Is that going to be an interest for the substation operations that we are expecting in the future, that the world is going to rely only on the digital substations? Yes.
So I tried very hard, but acoustically it was almost impossible to understand you. So I'm lost here. I couldn't really understand it.
Yes, so I'm just wondering, is because we saw how the benefits from the digital substation, and I'm wondering, is that something that we are expecting, is the world going to rely on the digital substations in the future?
I personally think that taken all together, these benefits should be convincing. When you pick out one of them and look only at one of the benefits, you can always find an argument that this one benefit is probably not worth doing all these efforts. But when you see the whole picture and you see that more and more promoted by the people involved with that, there is really something to gain from that. And so we expect that this topic is picking up.
Very well. And now we'll allow for one question for the gentleman. He's raising his hand for a very long time. So please, if one can assist me in handling my...
Thank you, Doctor, for the nice presentation. Actually, I have two questions. The first one, there is no doubt that the digital substation is promising and it is the future. Now, we are facing two challenges in deploying digital substations. The first one is the concern with the experts in our industry about the reliability of the digital substations. In fact, shifting the mindset from what the conventional system it is to the digital concept, merging all the secondary system in one fiber optic, going to that microprocessor. In fact, raise a question about several concerns about GPS clock synchronization, about other concerns raised in the industry. Now, to help the industry moving ahead with the digital substation, as you are part of SIGRI groups and maybe IEEE groups, have you come with a study about the reliability of digital substations compared to the conventional ones, so that you, the expert, could be encouraged to go to the concept of digital substation? Personally, at my level, we tried in multiple occasions to push for that digital substations, and we get this kind of concern from the experts. This is one part, and the other part also from economical point of view. Digital substation involved the non-conventional instrumentations, which basically increase the cost of the equipment cost. So the capital cost to build the substation became almost equal or slightly higher than the conventional substation. Yes, in the long run, the cost will be, because the operational cost is cheaper, but the capital cost is considered almost the same, which also impose a challenge to market the concept of the digital substation.
Okay, thank you for these extensive questions. I hope I can remember what you said. So first, let's go back a little bit on the reliability. I'm sorry, I have no detailed studies on that, but with all these redundancy concepts which are introduced here, I think it is possible to make a reliable system. There are means in this communication like this inherent wire checking for the goose communication and things like that, which are actually something that we did not have before, and we should not cheat ourselves about the reliability of the conventional systems. There are always loose contacts we do not know about. I think we can overcome that easily. So the second question was about the pricing, and there are some costs for the installation, but there are the costs for setting up the substation, and the wiring costs, I think, are something that I went into already. The maintenance costs are also something to look into, but you are right. It is surprising that this equipment seems to be more expensive, at least by now, even though especially the non-conventional instrument transformers would have the potential to be cheaper, yeah? But as of now, these are not mass-produced. These are almost hand-seamed single units, and I think we are not yet there where we get an economy of scale where we can really benefit from high volume production of that. I'm positive that this will level out in the future. And as I said, if you take only one aspect of these benefits, it is possibly not worth it. But if you take the whole packet, it is a different picture.
Thank you very much. So now we are going to the fourth speaker. So our next speaker is Michael Burke. Michael has received a first-class honor bachelor degree in electrical engineering from University of Cork in Ireland in 2003, and his master degree in electrical engineering power system with distinctions from the University of Bath, UK in 2009. He has 16 years of experience in the electrical power system industry, primarily in the power generation, transmission system operations, and electricity market and smart grid control systems. He is presently a senior power systems engineer at Saudi Aramco, focusing on the generation and grid interaction and associated control systems. So, ladies and gentlemen, please assist me in welcoming Michael to the stage.
I'm going to use the microphone as well. Good morning, everybody. Sabal Khair. My name is Michael Burke. I work in Power Systems Engineering Department of Saudi Aramco. Today, I'll be talking to you about smart grid control systems or power management systems for industrial power networks. The first half of the presentation, I'll talk, generally about these types of systems, the modeling and the testing that we do with those systems. And then in the second half of the presentation, I'll delve into a couple of really interesting case studies from Saudi Aramco. I'm delighted that Fred talked about the network because I don't have time to mention that in my presentation, but it goes without saying that a redundant, robust, fast communications network underpins all of this functionality. So what are the various applications of smart grid control systems? Well, there are three main areas. The first one, which interests us in Saudi Aramco, is the heavy industry, such as oil and gas or mining. So typically here, we want to maintain production when we get disconnected from the main grid, and Saudi Aramco has several sites where we have our own internal power generation. So it's all about maintaining production and moving towards a better relationship with the grid, being a service provider. At the utility level, typically we use the term remedial action scheme or special protection scheme. So the focus can be about blackout prevention, but more typically it's about optimizing the transmission system. For example, if we want to ship a large amount of renewable energy from a remote area to a load center, instead of building costly infrastructure, we can use a remedial action scheme to help us maintain N-1 security. And finally, we have the microgrids, which is an increasing trend towards energy independence and integration of renewable energy for small sites, such as university campuses, business parks, and so on. So these are the three main areas, and in general, we'll see that the control systems are very similar across the three different strands. So what's interesting about industrial grids and microgrids? Well, the thing that might surprise you is that they're actually quite similar. The characteristics of both grids are almost identical. Typically, we'll have some in-house generation and load, and the key feature is that we want to maintain security of supply, continuity of supply, whether we're connected to the main grid or whether we're isolated from that grid. The key characteristic and the thing that makes our control system so interesting is the low inertia of the industrial grids and the microgrids means that we get very fast changes in system frequency and voltage after a disturbance. For example, if we have an idling event, we'll see very fast rate of change of frequency. And as a result, our control systems need to have very fast actions. We're talking, less than 20 milliseconds, 30 milliseconds processing times to balance supply and demand. So as I mentioned, in the industrial sphere, we use the term power management systems. So what are the functions of this type of system? Well, again, they're almost identical to what you'll find in the IEEE standard 2030.7 for microgrid controllers. The first function is generation control. Particularly if we're isolated from the main grid, we need to control our system frequency, our system voltage 24/7. We can't rely on the utility to do that for us. If we are connected to the main grid, then, for economic reasons or for other reasons, we may want to control the amount of power that we're importing or exporting from the grid, or, as being a good actor on the transmission system, we want to provide a nice voltage or a nice reactive power at the point of interconnection. Secondly, we have fast load shedding. Because of the fast changes in system frequency on the industrial grid, we take preemptive action. We don't wait, like on the transmission system, until the frequency drops. We'll actually monitor circuit breaker statuses, and as soon as we acknowledge a disturbance or find a disturbance, such as loss of generation, loss of an interconnection, we'll trigger load shedding. Because we can't wait. The frequency is changing so fast, we can't take the chance and allow it to drop. Of course, we will have a backup under-frequency load shedding system, just in case our fast load shedding is not sufficient. If we're exporting a large amount of power onto the grid, then we're worried about over-frequency. It's the opposite problem. So if we lose that interconnection, the frequency is going to rise dramatically on our system, and we want to avoid blacking out on generator over-frequency protection. So typically we'll have a generation shedding algorithm or fast runback, which is a very fast control to our turbines, overriding normal ramp rates to balance generation and load. And of course, if we get disconnected from the main grid, we want to be able to reconnect without de-energizing our microgrid or our industrial grid. So auto-synchronization functions allow us to do that, to control the multiple generators in our grid, bring the frequency and the voltage back into sync with the main grid, and bring us back to our starting position. So, how do we prove it all works? Well, unfortunately, the types of scenarios we're talking about, like islanding and large generation trips on microgrids, are very difficult to test in real time. And even if we're allowed to test them, we may only get to test one or two scenarios. We don't get to test all the sort of corner scenarios, the difficult ones. So what we do to prove our systems is we make use of an advanced type of testing called real-time hardware-in-the-loop simulation. So in this simulation, we have a power flow model, a dynamic power flow model, running on our RTDS simulator. We feed the output from that model, the circuit breaker statuses, the frequency, the voltage, and so on, like field data into our physical controllers. We can trigger disturbances in our model, and we can assess how quickly our controller is detecting those disturbances and whether it's responding correctly. And of course, the final link in the chain is detecting or analyzing whether our power system is responding correctly and is stable to that disturbance. So it's a full circle of testing here, which gives us a real confidence in our systems. Okay, I mentioned testing, modeling. I mean, it goes without saying, garbage in, garbage out. If we don't spend the time perfecting our models, particularly our dynamic models, such as our governor models for specific peculiarities related to typical different fuels, for example, or different governor modes. For example, in islanding, we often change the governor mode to isochronous mode. Also, we need to make sure that the excitation system is measured or is modeled very accurately to ensure that we're catching any potential overvoltage situations. So it's important to note that because of the fast changes on the microgrid or on the industrial grid, we need to pay real attention to these models. They need to be very, very accurately tuned to make sure that we're catching all possible scenarios and giving us full confidence that our grids can survive these onerous conditions. And of course, if we can do comparisons with field test data, then that's the highest level of validation that we can give to our models, so that's definitely recommended. Okay, so that's the first half of the presentation, the general part. Now I'm going to jump into two case studies from Saudi Aramco. The first case study is an island grid feeding a large oil and gas facility in a remote part of Saudi Arabia. It's an island grid. It's not connected to the main electricity network. We have an existing power management system at the site running successfully for about 4 years. It's controlling the generation, frequency, voltage, and so on, all those functions that I mentioned earlier in real time. We also have a local power control center where we perform remote switching, generation dispatch, and our staff interact with our system and make settings changes as necessary. So what's interesting about this system is that it's just recently been selected by the National Renewable Energy Laboratory in the US to run in their microgrid testbed center. So, you know, we can say that Saudi Aramco and industrial grids are actually ahead of the curve when it comes to smart grid control systems. So what's new? I mean, the system has been running really well for 4 years, but like any good control system, it has to evolve to meet the operating conditions of the grid. In this case, our grid has been designed for a future load scenario for expanded load, and right now we have a situation where the grid is relatively lightly loaded. Because it's lightly loaded, the grid is actually generating reactive power, which under certain scenarios, in low load scenarios, can potentially lead to high voltage. And this is something that will become a challenge for the transmission grid as well in years to come, as the renewable energy comes in at the distribution level, removing the load and also removing the traditional sources of absorbing reactive power. High voltage is becoming more and more of an issue. So what's the solution? Well, our current voltage control paradigm is the traditional one, where we use the generators at the 69 kV to control that voltage, we use the generators at the 115 kV to control that voltage, and so on. What we're proposing here is to introduce a new control algorithm to provide a global megavar control, using all the generators at the different voltage levels to control the grid voltage. And again, this is something we're seeing now with active distribution networks, where distributed energy is being used to control the transmission system voltage. And of course, the whole goal, the end result here is to improve system security. Well, does it work? Yes, it does. We've done a lot of extensive simulations on our hardware-in-the-loop simulator. Here's a very simple example, or a small example from a low-load scenario. So you can see that the megavar profile from the local voltage control is a little bit unbalanced. Because of that unbalanced megavar profile, sometimes, for severe contingencies, we're insecure. Whereas with the global megavar control, we have a much more balanced profile, a much better allocation of megavar reserve across the grid. And based on our studies, we can show that for severe contingencies, instead of blacking out on V over F or overfluxing protection, in actual fact, we're able to ride through and restore the voltage to a normal level and maintain production. So this is really interesting that a small tweak in the control system has basically enabled us to avoid blackouts in certain scenarios. Moving on to case study number 2, it's a large refinery and power plant in the southwest of Saudi Arabia. We have 5 power blocks on site exporting between 2 gigawatts and 2.5 gigawatts onto the national grid. So it's a huge export onto the grid relative to the internal load of the plant, which is about 1 gigawatt. One of the interesting features when it comes to modeling is that the units at this power plant are running on a synthetic gas, which is generated within the plant. That gas has a very low heating value, and it presented some particular challenges when modeling the governor of this unit. So I'll talk briefly about some of the key features of our power management system at this site. We have what's called utility interface control. We can enter the target dispatch on the interconnection to the grid into our power management system, and it will work to allocate the various targets to our 5 power blocks and ultimately to the 15 turbines on the grid. Similarly, for voltage control, we can enter a target for a megavar or a kV at the point of interconnection, and our power management system will control the excitation systems of the 15 generators to achieve that target at the interconnection. So here's an example of how the industrial plant can change. Instead of being a bad actor just sucking reactive power from the system, here actually we're helping the grid, providing services to the grid, helping it with, for example, renewable integration. Okay, islanding detection and control is another feature we have. As I mentioned, we want to maintain production if we lose that interconnection to the grid. In this case, it's 2 gigawatts. So what happens if we lose that interconnection? Well, generation is now much greater than demand. So as I mentioned, because we have a small system, the frequency is going to rise dramatically. And we want to avoid blacking out on overfrequency, which is about 62.5 hertz. How do we achieve it? Well, we monitor the circuit breaker statuses of the interconnection both at our end and the transmission system operator substation end. We use very fast communications using a combination of hardwired control signals, IEC 61850 within the substation, talking to a front-end processor, ultimately to our controllers. Our controllers are taking very fast actions to trip generation and run back generation, which is a very fast control to the turbine, overriding normal ramp rates. And this, we can show that we can actually survive the loss of that interconnection, that huge export to the grid.
Michael, you got 2 minutes.
Okay, thank you. Last couple of slides. So here's just an example from our real-time digital simulator testing. On the top, we have the HMI from our power management system. In the pre-event scenario, we can see how our system would react. In this case, it would shed 2 gigawatts, so trip completely 2 gigawatts post-islanding, and run back 500 megawatts. And it's quite amazing to see that in this case, the frequency rose quite dramatically after the incident, but because of the fast actions in about 30 milliseconds processing by our power management system, we were able to return that frequency and damp it back down to the nominal of close to 60 hertz. So for me, this is really interesting because I'm sure, if most people asked you, could we survive islanding with an export of 2 to 2.5 gigawatts, you would say no, but actually with fast control actions and smart control systems, we're showing that we can actually do that. Okay, so just to wrap up, I've mentioned several different aspects of these control systems, but the key point is with rigorous testing, rigorous modeling, and fast control actions, we can show that power management systems can prevent outages, which is really what our job is all about. So thanks very much for your attention. I encourage you to read the paper and come to me afterwards if you have any questions on the topic. Also, I want to mention my co-authors who couldn't be here today, Dr. Abdurrahman Khatib and Dr. Ninian Chai from SEL in the US, and also Dr. Hussein Ben Ali from Saudi Aramco. Thanks very much.
Thank you very much. It's always a challenge to see how we deal with the microgrid, and I don't want to take more time from the audience to ask questions, so we may jump to the audience directly and see if there is an interest for questions to Michael. All right, so we'll move to the fifth speakers. So our fifth speaker is going to be Giorgio Fargi, and Giorgio has received his master's degree in electrical engineering from the University of Technology and Economics in Budapest, Hungary in 2008. And he received also an MBA from the University of Southampton, London, UK, 2018. His employment experience included Hungarian TSO, McDonald Limited, and TNEI Services Limited, Saudi Aramco, and Siemens. Giorgio currently has been acting as the Vice President of Software Product House and Consulting for the Middle East. So Giorgio, you are welcome to the stage.
Okay, Assalamu alaikum. Good morning, everyone. Thank you for the introduction. My name is Gergő Várhegyi. I'm working for Siemens based in Abu Dhabi in the UAE, acting as the Vice President of the Software Product House and the technical consulting business. The topic I brought today is about integrating wind farms, integrating renewable energy sources into the power grid. And how do we do that? How do we plan it? How do we prepare for it? We all know that the governments of the GCC countries, and not only the GCC countries, everywhere else in the world, they are changing the philosophy of running the economy or running the power generation, running the power grids, and there is a shift towards renewable energy sources. Why is it important? And why is it important, especially in this part of the world? At the moment, the Middle East is running, I would say, almost 100% on fossil fuel-based power plants, which is nice and neat, but the power demand is growing rapidly in this part of the world, much more rapidly than anywhere else, which means that in a few years' time, if we don't do anything, or if nothing is done, then all of the natural resources of oil and gas is going to be burnt in these low-efficient fossil fuel power plants, and that's going to impact the economy. So unless some shift is happening, bringing renewable sources to the power generation mix, there could be issues coming up sooner than later, actually. What are the problems, or what are the challenges that come into the renewable energy integration? The major problem is that, or actually the good thing is that resources are available. Yeah, but resources are not always available, like in a fossil fuel power plant. If you think about a solar farm, the sun is up for 9, 10, 12 hours a day, and then it goes out, and then basically those power plants are not generating anymore. There are sandstorms in this part of the world, right? If you have a solar power plant, let's say a significant large installation of 1 gigawatt or 2 gigawatt, and in a few minutes a sandstorm is coming, and the production of the solar farm drops down by 60, 70, 80%, then you have a big trouble, or anyone has a big trouble, because significant amount of generation goes out, and then we have a load generation imbalance, we have frequency issues, and that's just Michael shared. Being able to control those problems is actually a key point to keep the system up and running. So what can we do? We need to make sure that at the very early stages, when we are talking about integrating renewable sources to the grid, we start planning for it. We need to assess how they're going to behave once they are connected to the grid, whether they can provide the right amount of active and reactive power control, whether they be able to export really their capacity to the grid, the power that they are generating, whether they can contribute actually to support the grid when it comes to disturbances, outages, fault scenarios, and so on and so on. And to do that, what we need to do is to conduct a series of sets of studies before actually getting these plants connected. What they normally call is the grid code compliance studies, and there are several aspects that we need to test. So there is a small summary here. I'm going to speed up these slides and rather talk in details about the technicalities on the results page, because I think it's more interesting than reading the slides. One thing we need to check, short circuit ratio. Of course, it tells basically how tough is the grid where we are planning to integrate a renewable facility. Renewable facilities could be associated theoretically with control stability issues if they are connected to a weak network area, which means that we need to ensure that if we are plugging in a renewable source, a wind, a solar, whatever else, or a hybrid solution, the grid is tough enough over there, so that the point of connection, there will be no issues with stability and control. Steady state aspects. We have a new power generation facility. Can we export the power that is generated to the grid? Can we maintain voltages in the grid? Can we do the export under various voltage scenarios? The voltage varies in the network, and then if you think about a high voltage network, we have typically plus minus 5% voltage variation. Are we sure that the renewable facility is able to export the full capacity under each of these plus minus 5% voltage scenarios or not? Then it comes down to short circuit level. Short circuit levels are critical. Short circuit levels can be a problem in many cases. We've seen in few distribution network companies in the UAE especially talking about D1 network. They already have very high short circuit levels. So if we add generation to the network, short circuit level we are increasing. Therefore, it needs to be checked whether connecting the facilities would actually hurt or not the existing issues with the short circuit levels in the grid. Steady state reactive power compliance. This is what's shown actually on the picture here. We need to ensure that the renewable facility or the power generation facility is able to support the voltages in the grid. Luckily, with the latest technologies, with fully converted or converter-based connection of the renewable sources to the grid, we have a good control mechanism or control capacity from the converters to be able to control the voltages. Therefore, it's in a better stage with the current technology than it was, let's say, 5-10 years ago, when only induction machine-based wind turbine generators were available, which would require significant amount of reactive power compensation. And then comes down to the time domain simulation. We have an issue in the network. We have a drop or a loss of a fossil fuel power plant. We have a loss of a load center. We have a loss of a heavily loaded transmission line. We have a fault, for example, at the point of connection of the renewable facility to the grid. Is it surviving? Is it going out of synchronism? Is it providing the required amount of voltage and reactive power support during these voltage dips, during these fault events? We all need to check that. And last but not least, we need to talk about power quality issues. Most of these facilities are connected at 33 kV level, 33 kV collector system, and then directly stepped up to a high voltage transmission level, which means that any power quality problems coming from the facility with one impedance level up goes to the transmission system. And one thing we don't want to see is power quality problems at transmission level, because it can cascade down to the entire system. So, what do we need to do? We need to do simulations. To do simulations, we need to model the whole setup. We need to model the renewable facility. We need to model the external grid. And this is crucial. How do we model it? We've seen in few countries, without mentioning names, that they were using some general, some high-level models for assessing performance of individual renewable installations. And later it turned out simulation models were providing results that were not really applicable because the models were wrong, the simulation was not done in a correct way, and therefore those countries seen newly connected wind farms continuously tripping from the grid. And then the whole 400 megawatt of wind farm was shut down, new sets of simulation needed to be done, and then identified that additional compensations equipment was needed at the end, which they didn't really pick up in the first studies. So for that reason, it's important that we model everything in a correct way. Anyway, the subject wind farm we are talking about here is a 57 megawatt onshore installation, individual turbines with the respective step-up transformers, the 33 kV collector network marked with the orange cables, and then stepped up to a 400 kV, first to 132 kV, and then a cable goes down to the 400 kV substation, where it goes to transmission level. First sets of simulation results, I would rather show the picture. This is a kind of thermograph that shows the voltage profile across the wind farm and the point of connection. So we can see the scaling on the left-hand side. As long as we are in a greenish area, it means that the voltage is around unity, around 100% on 1 per unit, whatever we call it. So it means that the wind farm is able to export basically its full capacity of 57 megawatt under a nice, neat voltage profile to the grid. Reactive power compliance. This is one of the most critical issues when it comes to renewable sources. You see the red graphs, kind of weird-looking graphs, which basically describes the requirement of the grid code. It says that if we have 100% active power output coming from the wind farm, we need to ensure that the wind farm can provide leading as well as lagging reactive power, so it can generate and absorb typically 95 PU power factor at the point of connection. And as the active power capacity drops, the limits are changing. All in all, it's described with this red curve. So what the simulation results showed, you can see it on the green, the blue, and the orange curves, both for generating and absorbing reactive power, considering various voltages at the point of connection. So what the graph says, that the capacity of the wind farm is basically outside of this curve described by the grid code, which means that it can cover the full grid code requirements, therefore no additional equipment is needed. If any of this curve would be inside the red area, then we would need additional support. Whether we need additional reactors or capacitor banks, it's another question. Depends on we have issues on the leading or the lagging side of the reactive power. Let's go forward. Dynamic simulations. So 4 different scenarios are developed, each considering various fault or various voltage dips, if you like, for various durations at the point of connection where the wind farm is connected to the HV network. The first one is a 3-phase voltage fault. Voltage at the 400 kV network goes down to 0, stays 450 milliseconds. And then the wind farm, as we can see on the bottom, still producing active and reactive power as it should be. So it basically survives the dips. And then obviously the smaller the voltage dips are, they can last for the longer duration. And then the wind farm in each case were able to connected to provide active power as well as to provide reactive power through the converters to support basically the voltage dips during these periods. So all in all, it suggests that the wind farm had a good controllability and capacity to support the stability of the grid, if you like. Harmonics. Harmonic scan profile or frequency resonance scans profile on the first graph. It doesn't show, it's actually a surprising case. Usually we can see some parallel peaks or parallel resonances in the network, especially if we have an installation which connects.
You get 2 minutes.
Thank you. Where we connect power transformers and long cables. But in this case, it was a lucky situation. No significant resonances were observed. The bottom graph shows the harmonics coming to the 400 kV network. The green bars are basically the actual harmonic levels, and the red ones are the limits defined by grid codes. We can see that there is no violation in any of the harmonic orders starting from second to the 50 order. And the last picture on the right upside shows the harmonic injections at the individual turbine level. We can see that at the 48 and the 50 order, there is some limit violations, but since this is a 0.69 kV level at the turbine side and then the large harmonic orders, it basically doesn't hurt anything in the network, so we can just simply leave with it without really doing additional capex expenditure to mitigate this problem. So all in all, this was just an idea to show that what are the things that we really need to consider before connecting any individual renewable installation to the grid. Many things need to be done. Many things need to be done through proper simulation, from proper modeling to ensure that when it's really going to be connected, it's going to work and it's going to work as we want it to work. Thank you for your attention, and if any questions, please feel free.
Thank you very much. It's good to see how the static and dynamics requirements here in the wind farm, and due to the time constraint, we'll jump to the questions to the audience right away. So please, if you have any question to Gergio, just raise your hand. Please, gentleman from the back.
السلام عليكم. دكتور عبد الله أبو بشيد جامعة الملك فيصل King Faisal University. Did you, in your study, did you consider a specific type of wind turbines? And do you think it make difference if you use synchronous versus induction?
It was a Siemens Gamesa wind turbine type, 2.7 megawatt each. But it actually does make a significant difference which manufacturer you are talking about, because each of these manufacturers has each of its controls. And then we really need to see during these compliance studies whether the actual manufacturer's actual simulation model, how it provides the answer to our questions, and how it ticks all of these grid code compliant boxes. Sometimes it happens, I've seen it before, that few manufacturers their turbine was working fine, for example, in a European market, but they were struggling in a US market because the requirements put by the operator against these renewable facilities were different, and they couldn't meet these requirements. So then we had to go back and then see if there was a way to really redesign the controls of these individual units so they are able to be compliant with the other market requirements.
Thank you very much. It was well presented. So now we'll move to the six speakers. Our six speakers is Mohammed Al-Nassar. Mohammed obtained his bachelor degree from King Fahd University of Petroleum and Minerals in Electrical Engineering, and his master's degree from the same university, from the University of Toronto, Canada, while his PhD from King Abdullah University of Science and Technology. Mohammed published a couple of joint journal articles, including the IEEE Transition, Natural Scientific Reports, and the Advanced Electronics Materials. He's currently working with Saudi Aramco at the Power Systems Planning Department. Mohammed, you are welcome to the stage.
Assalamu alaikum, everyone. It is my great pleasure to speak to you today. The title of my presentation is about the impact of renewables on the kingdom's utility fuel mix. This work is based on a simulation optimization, which looks into the long-term effect of different renewable penetration levels on the utility fuel mix. Before I proceed, I would like to acknowledge the contribution of my co-author, Santiago Arango, who exerted tremendous amount of effort in setting up the simulation cases. So, starting with the agenda, first the presentation will start with a brief introduction and motivation of this work. Then I will highlight to you the modeling approach that we followed along with the simulation assumptions, or the major assumptions that we considered. Then we'll highlight the different scenario cases, renewable scenario cases that we considered. And after that, I will share with you the results and briefly discuss them. And in the conclusion, we'll summarize all the results we obtained and then give some key takeaway points. So, renewable energy are becoming cost competitive compared to conventional thermal power plants. And when in the not far future from now, they may set the ceiling price for the electricity in many markets. And here in Saudi Arabia, we are very well known for our hydrocarbon reserves. However, when it comes to renewable energy, that's not the case. And here where the kingdom's Vision 2030 came in, and introduced a 9.5 target as a renewable first initial target, and classified renewable energy as one of the pillars that will expand the economy of the kingdom so that it is not just pure oil. So, Vision 2030 is the main driver. What about others? We know of the declining cost curve of renewable energy. Of course, with the time, the cost of the technology comes down, and we've seen the world record-breaking bids of Sakaka and Domat al-Jandal, and which became consequently a catalyst for the acceleration of the kingdom's renewable energy program under the Renewable Energy Project Development Office by increasing the targets to roughly 27 gigawatts in the next 5 years and 58 gigawatts by 2030. On the other hand, we got the Ministry of Energy is keen toward preserving our hydrocarbon resources toward more value-added utilization. And in fact, many energy conservation programs are being worked out through energy price reform and fuel switching or swapping programs. And last but not least, we know that renewable energy will be a key player in decarbonizing our energy sector, and leading to low CO2 emissions. Let's take a look at last year's fuel mix, 2018, where we can see the majority of electricity produced came from gas, followed by crude, and then followed by heavy fuel oil, then comes diesel with almost no contribution from renewables. What we'll be looking at here, we will be looking at different renewable scenarios on the effect on this renewable hydrocarbon fuel mix. Now, coming up with an optimized energy mix is a demanding task and often requires adequate methodologies and sophisticated modeling tools. And what we used here, we used the Plexus integrated energy simulation tool. And we used the Plexus, if you are aware, it is an integrated energy tool which is capable to do the production modeling, maintenance optimization, and market assessment, as well as the long-term expansion plan, which we used here. The long-term expansion plan finds the optimum combination of generation new builds, as well as the plant retirements, transmission upgrades, to come up with the most economical combination leading to the least cost of the system, or basically minimizing the net present value of the total cost of the system by looking at long-term planning horizons. What we're looking at here, 11 years, we'll focus on 11 years from now, that is year 2030. On the right side, you can see the list of the major assumptions we've considered. We've considered 3.8 demand growth, moderate growth rate. And we've also set the retirements for the modeled units based on the technical lifetime. And we've also assumed the energy price reform to take effect, to liberalize the liquid fuel cost and make the gas cheaper fuel. And based on that, we've assumed a couple of plants within the proximity of our master gas system to burn gas in the future. These are the three cases that we've considered, basically setting up the envelope. We have the first case, the base case, open optimization case. We impose no limit. We let the software bring renewables as much as it can if it's economical. And the second case, we've called the REPDO case. What we did here, we allowed the software to bring the renewables, however, not to exceed the recently announced REPDO targets, the 5 years target, 27, and the 2030 targets, 58 gigawatts. And we've asked ourselves, what if the project delays we've encountered, what if plans did not materialize? We've considered a low-profile case where we imposed an annual limited amount of renewables that the software can take. And we'll show you the details of the breakdown. And by that, we've set up the target for the 5 years to be 14 gigawatts, and the 2030 target, 43 gigawatts. Just to have some insight about the REPDO case, if you know the REPDO and confirmed projects is around 13 to 14. So what we did in the second case, we forced these targets to be minimum, and then allow the program to build on top of them, but not to exceed the 5-year target 27 and the 2030 targets. This is the details for the low case. We only considered the projects that are under construction right now, namely Skaka and Domat Al Jandal, only 700 megawatts. After that, we've introduced small incremental annual incremental, we call them constrained annual additions, starting roughly with about 3 gigawatts. And then we've relaxed this limit or constraint over the years, assuming local manufacturing are in place and assuming the expertise are gained to conduct such projects. And that's the breakdown, how we reach up to the 14 gigawatts in the next 5 years and the 43 gigawatts. So let's jump into the simulation results. Let's start with the open optimization. So the renewable build-up cases, as you can see, we see the system brings in renewable as fast as it can, with a sharp increase over the first coming years, reaching to 50.7 gigawatts in year 2030. If you notice here, thermal additions are not being brought into the system only in 2025 onwards, and it's bringing it slightly. The effect of this renewable buildup that we've got on the hydrocarbon fuel mix, we can clearly see that as soon as renewable kicks in 2020, at a very fast rate, we can see a huge reduction in the liquid hydrocarbons, and then all the way to 2030. So what does that 50 gigawatts that we got means in terms of liquid displacement? This is approximately 200, the 50 gigawatts will be displacing 255 of thousands of barrels per day of oil equivalent. To translate that 50 gigawatts that we've got into energy contribution towards the total terawatt hours required in the system, we've calculated that to 28%. And on the right side, you can see the chronological evolution of the fuels over the years, and see how you can see how renewables are advancing, becoming contributing a lot to our energy, and how the other liquid fuels are drastically reducing. Moving on to the second case, the Repto case. This is the renewable build-up profile that we've obtained. Not so far from the base case, although meeting the 27 target in the first 5 years, however, reaching approximately similar capacity of renewables, 49.6, and similarly, the thermal additions appear from 2025 onwards. Effect of this renewable profile on the fuel mix is similar to the previous case. However, only the reduction rate of the liquid fuels slightly lower. Now, since also the liquid displacement, since it is approximately similar to the previous case, so 49 versus 50, so the displacement potential is around 251 MBDOEs. In terms of energy, we expected the same energy contribution. Here we get the 28% from renewables, and the gas is 58. I leave you with the chronological evolution of the fuel mix. The main difference with the previous is just the rate at which liquid fuels are being displaced in this case. All right, let's do the last case, the low case. Renewable, because
Dr.
we've said...
Nassar, you get 2 minutes.
All right, I'm almost there. Since we imposed the constraints, this is the renewable build-up profile, and it reaches the limit that we've set. And thermal additions are being brought more and an 1 year early stage. And effect on the displacement, we can see as soon as they kick in, they will start displacing liquid, but at a much, much lower rate. Liquid displacement potential due to this 43 gigawatts is almost 200 MBDOEs. Energy contribution is dropped to 22%, and you can see the evolution, chronological evolution of the contribution from each source. Definitely, you can notice the slow rate of liquid displacement, especially for the crude and heavy fuel oil in this case. Let's take a look at the results of these simulations and put them all in one graph. So what we can see here, what this graph tells us is that it is more economical to bring renewables as soon as we can, rather than waiting down the line and miss out on the displacement of the high-value fuels. And also what this tells us is that regardless of the build-up cases, there is an optimal down the road, optimal level of renewables that optimally minimizes the total system cost, roughly around 50 around here. So to conclude, this is the table summarizing the results from the different simulation cases where we can see the different renewable penetration or the capacities obtained, the 5 years and the 10 years or 11 years, along with the percentages from each technology, and the effect on the right side on the hydrocarbon fuel mix. So what we can say here, that renewables will become a major player in our fuel mix, and the more we have, the more liquid display, more fuel that we will displace, and the less CO2 emissions we put. And in the long run, renewable penetration levels tend to converge. And this is, again, purely based on theoretical exercise. Of course, this will depend on demand materialization, policy enforcement, and government incentives. And sales gas will continue to play a dominant role in the future of the utility mix. And last but not least, as we deploy more and more renewables, we need to pay attention to the physical and technical constraints imposed in the system, which lead us to the topic of power system flexibility solutions. And I believe my colleague, he has a presentation in the afternoon. He will tackle this challenge and how to overcome it. With that, I conclude, and thank you so much.
Thank you very much, Dr. Nassar. It struck me that you present a real practical example that I deeply was involved in, and that raised to me so many questions that I want to ask, but I will leave that room to the audience. So please, if there is anyone from the audience want to ask questions to Dr. Nassar, please raise your hand. Please.
Assalamu alaikum, Dr. Abdurrahman Al-Dhaibi from CACST. Did you consider nuclear in your presentation because it's going to be added up to the fuel mix?
Yes, nuclear is considered. Maybe we just, the label here was U-235, which is nuclear, uranium, yes.
Thank you very much. So we'll move with our last speakers, which is going to be Engineer Badr Al-Atabi. Badr, he has an extensive 18 years of experience working with Saudi Aramco. He graduated from King Fahd University of Petroleum and Minerals in 2001 with a bachelor degree in electrical engineering, and got his master degree by this year in sustainable energy from KFUPM also. So please, you are welcome to the stage, Badr.
Assalamu alaikum. Good morning, everyone. Thanks, Asim, for the introduction. My name is Badr Atabi, working for Saudi Aramco in project management. It's a great pleasure today to stand before you, sharing with you the results of the techno-economic study performed to examine the supplying Saudi Aramco facility with a photovoltaic farm. Before I start, I want to recognize the effort of the co-authors of the paper, Dr. Mohammed Abidu from KFUPM, Engineer Mahmoud Jalaluddin, Saudi Aramco, Engineer Muhannad Al-Nuwaisir from Saudi Aramco also, and Engineer Ali Al-Qahtani from Saudi Electricity Company. So this is the arrangement for today's presentation. First, we'll have the introduction. In the introduction, we'll be discussing 2 points: the challenges faced on the remote grids, and then the available alternatives. Then we'll highlight the potential of the PV in the kingdom. Then after that, the objective of the study will be detailed in section 2. After that, the roadmap followed in the study will be explored in the problem formulation section. The methodology, the economic and technical studies will be detailed in the methodology. After that, the selected facility will give a brief on the selected facility in Saudi Aramco in the case study section. The results and analysis. The results of the study will be detailed also, further in the results and analysis section. The sensitivity analysis performed on some of the system parameters will also be discussed in the section of sensitivity analysis. Then the summary of the study results will be in the conclusion section. So to start with, the remote off-grid systems are faced with some challenges. Those challenges are, or even integrating the renewable resources with the conventional thermal generation. I don't want to spend much of time on this because Dr. Anassar highlighted the potential of PV in Kingdom. However, there is a world record achieved by Dubai recently in the Gain Solar Park, achieved about 1.7 cent per kilowatt hour for the PV energy. So the objective of this study is to evaluate economically and technically supplying an existing Saudi Aramco facility, mainly it's a pumping facility, with a PV farm. The PV will be a new installation. The generators are existing installation, and due to the criticality of the facility, generators have to be always online. We cannot depend only on PV. So this, taking into consideration these constraints, these are the possible themes of the system. We can have gas generators only, gas generators with PV, or gas generators integrated with PV and energy storage. Evaluating these different possible schemes economically and technically, the most optimal scheme will be selected based on two factors: the net present cost of the scheme and the lowest levelized cost of energy. The design has to meet, since this installation is in Saudi Aramco, so the design has to meet Saudi Aramco standards. Some of these Saudi Aramco engineering standard requirements are as shown here. The inverter efficiency has to be more than 40% more in the designed capacity, need to be considered. 20% for the derating factor, 10% for the aging, and additional 10% for expected future growth. So these are the steps we followed in performing the studies. We first evaluated or identified 5 potential sites. Then we evaluated those 5 potential sites. Then after we shortlisted, selected the candidate site, we collected the data, such as the equipment data, the operational scenarios, and then selected after that the components of the PV installation, such as the PV model, the batteries, and the inverters. And then the economic evaluation was conducted after that, including the sensitivity analysis. As I said, we identified 5 potential sites. These sites were all evaluated against this criteria: the criticality of the facility, the electrification cost, and the electrification cost was an actual bid received from Saudi Electricity Company to electrify those 5 sites. And then the existing energy bill for each of these 5 sites, and then the operation and maintenance cost of each of these sites. The shortlisted site was found to be the highest in all of these criteria. It was the most critical, with the highest cost in all of the cost elements. So the economic evaluation software, we use an economic software to evaluate the possible schemes collecting or inputting the following information: the load profile, the fuel price, the generators data, operation and maintenance, and other data collected from the site. Doing the economics, we will have the net present cost, levelized cost of energy, and as I said, those are the two main factors that the optimal scheme will be selected based on. We also have the renewable penetration percentage, energy data, and other output of the economic software. Technical evaluation. We use the most optimal scheme as a result of the economic evaluation. We did a technical evaluation and integrating that optimal scheme into the utility model. So the utility model integrated with the PV and the storage system, integrated into the model of the facility, and then we perform the load flow studies. So the existing facility is basically a pumping facility with almost a steady load. The average is 1.75, sorry, the average is 1.56 with a maximum of 1.75 megawatt. It has 3 generators rating at 4.16 kV, 2 megawatt at a 0.8 power factor. There are two gas generators, 1 backup diesel generator. The loads are basically mostly are pumps ranging from 1 horsepower to 250 horsepower. And there are other loads, MOVs, lighting, gatehouse, and others. So the most optimal scheme was found to be PV, gas generator, and storage. Hybrid PV, gas, and storage. The finance of this system, the net present cost was found to be 13.9, and the levelized cost of energy was found to be $0.097 per kilowatt hour. The components or the scheme consist of about 9.4 megawatt PV modules, 1.8 kilowatt converter capacity, and 1 gas generator, existing gas generator, and 300, almost 400 strings of battery, 12 battery each. The load flow calculation, as you know, was performed to examine the voltage levels and identify the overload conditions at different configuration, different source configuration, and different bus configuration as shown in the slide. So the load flow study was found to be within the acceptable ranges. So this proved that the selected optimal scheme is technically acceptable. A sensitivity analysis on fuel prices was conducted on 3 values: the 9.6, 6.7, and 2.6 $ per liter. These values were obtained from the World Bank for the natural gas price forecast over the next 5 years. This is also a further analysis, sensitivity analysis, performed on the PV prices. The sensitivity analysis is to check the effect of the changing of those parameters on the system economics. So we did 2 scenarios from the existing scenario. We reduced the capital and replacement cost by 90% in the first scenario and by 80% in the second scenario. And the operation and maintenance cost was reduced 80% in the first scenario and 60% in the second scenario. Sorry, the 60% is not shown in the second scenario. So these are the results. What are the effects of those fuel prices and PV modules prices on the system economics. We can see here from the table that the fuel price has no effect on the net present cost, nor doesn't have much of effect on the levelized cost of energy, whereas the price of the BV has more effect on those net present and levelized cost of energy. And this is due to the fact, and we'll be discussing, illustrating this later, that we have a high penetration of renewables, and the gas generator did not operate for a long time during the year. It operated only for 10% of the time. This illustrates in a graphical view. We can see here very clearly that for a given fuel price, or across all the fuel prices, there is no much of change between the net present value and the levelized cost of energy. However, for one fuel price, if we take, for example, 1.2, we can see a difference in the levelized cost of energy within that fuel price. This is a further sensitivity analysis to check the effect of the depth of discharge of batteries on the economics of the system. We can see that if we allow for more depth of discharge, the economics will enhance. It's only the lifetime of the battery that will be reduced, but we need to consider other factors. We can see that.
Badr, you get 2 minutes.
2 minutes? Okay, sure. We can see the economics improved a lot in the return on investment, internal rate of return, and the payback period was improved by allowing for more DOD. Similarly, for the levelized cost of energy, improves with more DOD percentage. In summary, this study proves that the BV, the hybrid BV with the storage and gas generator, has reduced the economics by 37%, reducing the net present value, the net present cost for the existing system from $22 to $8 million, and the levelized cost of energy from 1.15 to 0.0975. That's the direct benefit. Indirect benefits are redundancy in the power supply and enhancing the environmental measures. This is in support to the 2030 vision in both energy and environmental sectors. Adapting such renewable generation within the kingdom is supporting the 2030 vision in energy and environmental sectors. Thank you. If you have any question, please feel free.
Thank you very much, Badr. We can allow for one questions to Badr. So please, if you have any question to Badr, just raise your hand. Thank you very much. So it was a pleasure hearing and observing all the scientific paper which was presented by the speakers. It was an interest of me and definitely interest of many of you. And here we conclude our session number 4. And before that, it's the time to award these gentlemen for their work and sharing the experience of that. Thank you.
ونحن بدورنا نشكر المهندس عصام القاضي وجميع المشاركين في هذه الجلسة، ويسرنا أن نبدأ في تكريم المشاركين في هذه الجلسة. أتمنى من معالي الدكتور خالد بن صالح سلطان رئيس مدينة الملك عبد الله للطاقة الذرية والمتجددة بتكريم المشاركين في هذه الجلسة. البداية مع مدير هذه الجلسة المهندس عصام القاضي. يلا شباب استنيني. الدكتور محمد علام. السيد أحمد عبد العظيم. الدكتور فريد شتاينهاوزر. السيد مايكل بورك. والسيد جورجو فورغي. السيد محمد النصار. والسيد بدر العتيب. شكرا لمعالي الدكتور خالد سلطان ولجميع المشاركين في هذه الجلسة. استراحة قصيرة لمدة ربع ساعة، نعود بعدها إلى الجلسة الخامسة. شكرا جزيلا لكم.
Ladies and gentlemen, we'll have a coffee break for 15 minutes.
السيدات والسادة، أهلا بكم مجددا إلى جلسات المؤتمر السعودي التاسع للشبكات الذكية 2019. جلستنا المقبلة ستكون تحت عنوان عصر جديد لسياسات أسواق الطاقة والكهرباء. فلنتعرف بداية على المشاركين في هذه الجلسة.
Ladies and gentlemen, welcome to the fifth session titled Markets and Policies for New Energy Era, moderated by Dr. Turki Al-Aqil, King Abdullah Petroleum Studies and Research Center, CAPSAC. First paper, Vision of Grid and Legal Developments for a RES-dominant power system in Saudi Arabia, presented by Osama Bidala, Elia Grid International. Second paper, Open Access to Electricity Networks and the Saudi Arabian Experience, presented by FM Novenara, National Grid. Third paper, Energy Analysis for Hybrid Wind Solar Facilities, presented by Adam Terra, UL. Fourth paper, Long-Term Viability of the Saudi Electric Utility Business Model, considering risks and opportunities, presented by Mohammed Al-Mudhi, KFUPM and SEC.
إذن رحبوا معي بمدير هذه الجلسة الأستاذ تركي، الدكتور تركي العقيل، وجميع المشاركين فيها. أهلا بكم.
يعطيك العافية أستاذ الفاضل. السلام عليكم ورحمة الله وبركاته. Welcome to session number 5, titled Market and Policies for a New Era. My name is Turki Al-Aqil. I'm from CAPSARC, and I'm honored to be the moderator for this session. Markets and policy for electricity markets. There is a paradigm shift in energy transitions, not only in this region, but also in the global context. The goal is to strike a balance between the economic growth, sustainable and reliable energy access, and environmental sustainability. Energy transition proposed by different characteristics. One of them is to decarbonize the power sector. And to cope with that change in energy transition, electricity market reforms had undergone different efforts in order to propose a new energy transitions that can attain the goals mentioned. Today we have experts in market reforms who will drive us into some insights that to be shared in different aspects of electricity market. To start with the first speaker, so our first speaker is Engineer Osama Bidara. Engineer Osama is the General Manager of Elia Grid International in Dubai. He will be presenting his paper that will tackle an approach for designing an investment portfolio to optimize investment selection. Engineer Osama has been working with the Elia Group since 2011. He was responsible for identifying and developing company activities in the Middle East region. In the frame of this function, he took part in several projects ranging from supporting local utilities on defining their long-term strategy, integrating renewable energy into the power system and optimizing asset management practices, and to leverage the hands-on experience of their mother company, Elia in Belgium and 50 Hertz in Germany, and the European best practices to provide pragmatic solutions to its clients. Bidara Osama holds a master's degree in electromechanical engineering and a master in business management from the ULB in Belgium. Please join me welcoming Engineer Osama. I'm sorry, before we start the presentations, we will work this way. We will have 15 minutes allocated for each presenter, and then we'll open the floor for questions. Please, Osama, the floor is yours.
Thank you. Thank you very much. This paper has been prepared in collaboration between Elia Grid International and my colleague Rita Allen. She'll be presenting some of the slides at the end of my presentation. So the context of this presentation is the following. So what we know is that Saudi Arabia is going through a shift. Today, the energy mix that you have is mainly composed of oil and gas, but the country is going towards a situation with more renewable. When you go for this kind of change, and then the targets are usually set, in this case, the target now are set at 58. Still there is some room for the way this will be implemented in the country. The location of those power plants is still to be defined. Some of them are already defined, but the coming one will still have to be defined. The percentage of each technology still has to be defined. This is creating some kind of uncertainties, which is a burden for the utilities that have to integrate the system, the amount of renewable in the system. The methodology I'll be explaining is allowing for utilities and also the government to prepare for this integration in the most cost-effective way. So the methodology we'll be talking about is a methodology that has different steps. The first one is defining scenarios. In this kind of discussion, when we're talking about scenarios, the idea is to identify what are the potential ways this renewable energy can be integrated, and that, of course, will have an impact on the power mix that you will have, but also on the structure of the grid that you will have to manage. Then we're defining the needs. From there, we identify the gaps between what you have today and the grid that you need to have in the future, but also the power system that you may have in the future. After that, from those situations, we identify the structure of the grid that you want to implement, and then we define the most cost-effective way to integrate or to build those assets, and then we find ways to optimally steer the portfolio of investment that you have to do on the long run. The idea behind this methodology is to continuously ensure that there is an alignment with the stakeholders, and those stakeholders are, of course, the ministries, but also the public, because some of the assets that you have to build are new lines and new investment that sometimes require an acceptance from the public to be built. So the first step that we are looking at are the scenarios, and when we are building scenarios, we are looking to 5 to 20 years with all the potential, say, uncertainties that you may have. Uncertainties, as I was explaining earlier, was, for instance, the location of those power plants, or the renewable power plants. It can also be some of the delays that you may face when you are integrating the renewables. All those elements can take into account and build different scenarios. And here we show examples of how, some examples of how those kind of scenarios can be built. The next step is to model that. And when we're talking about modeling, my colleagues earlier have explained using tools such as Plexus and Antares. The idea behind those tools is to simulate the way the generation will be used and running during different times of the years. So in that kind of cases, we are modeling the behavior of the renewables, but also the behavior of the classical generation with the objective to identify the least cost solution that will be used throughout the year. Here we have an example, for instance, that has been used for our cases in Belgium, where the black line is the demand that you have, the green is the production coming from the renewable, and the gaps are the opportunities that we have, for instance, in our country to be using storage units, for instance. When we are modeling the system, and in the past, when we were doing grid development, we are taking usually the maximum case and the minimum cases, and we base ourselves on that to define the grid of the need. But what we see nowadays, and especially with the renewable and the wind generation, the patterns are extremely changing. This is the case of what we have witnessed in reality in 50 Hertz, which is one of the TSOs of the group, where the fluctuation of the power per generation is so high that you cannot anymore just use usual models, which is the max and the mean, but then you have to model the entire behavior of the grid at different moments of the day and the time. Based on that, we run the two cases. So we run the simulation of the market, and we look at the impact of those generation on the system, and we identify the new needs. And when we say new needs, can be new additional lines, new interconnection, or new generation that is needed. And from that, we derive different cost-benefit analysis, and we rank the different solutions based on the one that is benefiting the most the community at the end of the day. Ultimately, what we notice when we do such kind of analysis is due to the fact that the renewable is the cheapest solution in terms of marginal cost, what happens is that the classical generation tends to be pushed back out of the unit commitment, and that is putting pressure on the investment, especially for foreign investment to be able to invest in classical generation because they see the generation not being used. And that has an impact on the way you're designing your PPA, but also the way you're designing your entire market system. So when we build the investment portfolio, we are looking at putting at the bottom all the needs that has, let's say, no regret actions, because in any kind of scenario, those kind of investment will be required. And then progressively, we are building the portfolio with solutions that can mitigate some of the investment that we have to do by delaying some of those investments so we can maybe cover them in another portfolio on a later stage. So this methodology requires to be implemented in utilities. We have done that in different TSOs, and that requires to adapt to the ways the different departments are working and the tools that are being used in order to be able to manage and to take the benefit from all those solutions. Next to that, those kind of solutions require an adaptation of the legal framework. And that I will leave the floor to my colleague, Rita Allen.
Osama. Hello everybody, salam alaikum. As Osama had mentioned, we are experiencing a paradigm shift, like Dr. Turki said, in the energy market, and part of those considerations involve a shift also in the legal framework. The current electricity grid is experiencing some integration and regulatory changes. In particular, the challenges are that the 60 Hz grid frequency limits the potential for support from neighboring countries in the sense that we see the restrictions on export and import due to that Hertz restriction. So really what we're hoping for is to develop a need and a robust legal framework to discover an appropriate supply and regulation of electricity in the market. And of course, the beginning has been made in that the small-scale electricity regulations for the solar PV systems are actually in place and have been a real success for the market. And we see similarly the private sector has a great interest in solar PV developments, as can be seen in the industry and dairy farms and so on throughout the kingdom. Our recommendation, of course, is that the regulatory framework for renewable energy systems can be developed further by consultation with experts in order to develop appropriate and effective grid balancing systems. Ultimately, that kind of implementation is likely to be ably supported by organizations providing regulatory assistance at present, like ECRA and KCARE, who are present today and who have some excellent information. This will allow for the appropriate expansion of the electricity grid throughout all of the exciting projects and areas in need. Ultimately, the conclusions we've touched on today are that the grid challenges and balancing systems, in hand in glove with appropriate legal support, will overcome the barriers in achieving the low carbon goals for the kingdom. Once the regulatory framework is adequately robust, we can suitably govern from a legal perspective the supply of alternative energy using renewable sources which are so abundant in this kingdom. This will enable a sound framework to support ECRA and KCARE and the government's regulatory ministries to provide a sensible basis for the expansion of all the electricity grid networks in a coherent manner throughout the kingdom, and ultimately the integration through the GCC to allow for import and export throughout the neighboring countries. We see this as a welcome development, and it is consistent with Saudi's Vision 2030 and its goal of a diversified economy, which is expected to increase the local energy consumption threefold by 2030, an amazing statistic. Of course, there are obvious solar and wind power potentials throughout the kingdom, and the plans for the expansion of renewable energies in this sector are very impressive. I'm interested to hear what our other speakers have to say about the challenges in the grid integration and thank you for the opportunity to speak with you this morning.
Thanks to both Osama and Rita for this informative presentation. Now we move to our second speaker, Engineer Ephraim Novenario from the National Grid Saudi Arabia, to walk us through a journey towards open access of other countries compared with Saudi Arabia's experience. Engineer Ephraim is a senior regulatory analyst and regulatory affairs division of National Grid in Saudi Arabia. He graduated from Adamson University in 2002 with bachelor's degree in electrical engineering. He graduated with a master's degree in electrical engineering from the same university in 2009. He has 17 years of experience in power system in the fields of teaching, electricity market, power industry regulations, and quality assurance. He worked in academic institutions in the Philippines, such as Adamson University, University of Birchbull Hill, University and Technological Institute of the Philippines. He worked in the Manila Electric Company, Meralaco, as quality assurance engineer. He also worked in the Philippine Electricity Market Corporation, the operator of Philippine wholesale market, spot market, wholesale electricity spot market, as training specialist. Please join me welcoming Engineer Ephraim.
Good morning. Thank you, Mr. Chairman, for that wonderful introduction. It's an honor to be part of this wonderful technical conference. My technical paper is entitled Open Access to Electricity Networks and the Saudi Arabian Experience. So, how can I control this? I'm sorry. How can I? What's moving forward? Okay. Sorry about that. The scope of my presentation is I will explain to you what an open access means, the experience of several countries that adopted open access, and the Saudi Arabian experience. So, the Saudi Arabian electricity law provides for rights among its customer the right to choose electricity supplier. And based on this example, you can see a transmission-connected customer that has a trading arrangement with the incumbent utility that owns the generation and the transmission system. So, the choice of electricity supplier only exists, number one, when there is a competition at the generation segment. And number two, if the monopolized transmission business allows or set to allow a fair and non-discriminatory access to the transmission system. Of course, it is very technically infeasible for a generator of choice to build his own transmission system to serve his contractual obligation to the customer. So based on this illustration, we can say that an open access is actually a key driver to competition. Of course, an access to the transmission system is bound by a transmission fee for using the system and adherence to the physical laws governing electrical transmission. So, several countries have embraced open access to the transmission service, and here I am laying down some key conditions that they adopted in order for them to implement open access. First off is restructuring. Restructuring is basically breaking the structure of the monopoly. Well, we can do that by organizational restructuring or functional restructuring. But basically the point is that for the whole system, for the whole system itself, we have to identify which part of the segment is competitive and which part remains to be a natural monopoly. Well, of course, generation and supply of electricity is a good candidate for competition. However, the transmission and distribution remains to be a natural monopoly because it is very difficult to create competing services among them. So that's why open access rules are established to create a sort of a competitive effect in a monopolized environment. So what it does is like it creates a pressure on the prices and quality of services of a transmission system in a very efficient levels. The regulation means ceasing to generate the prices of monopoly and introducing competition. And the last one is transparent pricing of energy and grid services. So what it means is that the cost recovery mechanism for using the transmission system shall be recovered in such a manner that it reflects the self-operation of the transmission business only, not by any means or no cross-subsidies. Here, I am laying down the landmark orders of mature jurisdiction that implemented the open access, and I'll start with the US with FERC 888 and 889, the UK with Electricity Act of 1989, the Philippines with IPIRA Law of 2001, India, Electricity Act of 2003, and Brazil, the 1995 Concession Law 9074. The Energy Policy Act of United States in 1992 was further reaffirmed by FERC 888 order and 889. Basically what happens was there was a platform devised in such a way that generators would be allowed to trade at the wholesale level, having a transmission tariff that applies to everyone. There is also a regulation and reliability council established in place to facilitate the monitoring of interstate trading. And also this act paved the way for the creation of electricity markets and independent system operators. So the choice of the consumer of electricity service is done in such a way that you can choose from contracts and enter into a mechanism that would allow for a transparent prices of electricity. However, there is a problem at the retail level wherein the customer's choice of electricity is in question. They tend to stay at the incumbent utility because they think that the incentives are not right. Now, moving on to the United Kingdom, they have Electricity Act of 1989 that basically restructured the previous monopoly in generation. And the open access rules of UK is embodied into their industry codes. They have a pool type market before the NATA and now move to a self-dispatch mechanism wherein the generators have the right to determine its schedule and subject to a balancing act by a balancing authority. Now, they have this feature of pricing their use of system that is priced locationally. It is driven by the cost of investment per location. And they decided in such a way that 27% of the use of system charges is levied to the generators and 73% to the demand. Now moving on, Philippines, due to a World Bank study, well, that study suggests that if we will not restructure our power industry, we may have scarcity in terms of generation. So that in 2001, IPIRA came into law basically just to restructure the power industry and creating competitive segments as well as natural monopoly out of it. So the main core of the law itself is, well, just like here, giving choices to the customer in such a way that the mechanism for determining prices of electricity and services are equally applied to everyone. So we have electricity market that trades, we have a bilateral contracts market It's a separate trading between the producer and the customer. We have energy market, ancillary services market. And one of the challenges we face is the privatization of government assets. Until now, we have not achieved 100% of privatization, and it's quite a challenge. Now, 5 years ago, we implemented retail market wherein the customer has a right to switch supplier. So in India, they have their Electricity Act of 2003, and basically it follows the same path as the previous experience. And they have a choice, they created a choice among their consumer, the choice of electricity supply, and they restructure their transmission tariff in a very reflective manner. So the customers are allowed to trade interstate and intrastate, and they can source the electricity from a long-term bilateral contract, as well as sourcing part of it from the power exchanges. Brazil, similar with some other experience that I laid a while ago, has their power concession law, basically to give an open access among the generators to the transmission system. Well, basically you can see the common path that they took. It's like opening access to the transmission system is like having clear and enforceable rules of managing the power flow in the transmission system. The transmission charges are open and non-discriminatorily mechanized and crafted. They have their bilateral contracts, and they divided the trading into free trading and as well as the regulated trading. Free trading means counterparties are allowed to trade by themselves based on the term that they decide on. Regulated trading, it is moderated, or I would say monitored by the government. Now, World Bank studies suggest that the open access implementation in Brazil is minimal, as they have seen that there is a lack of transparency in the ancillary pricing, in the ancillary services, because it is not designed in such a way that they can get all the advantages of having locational features of pricing, distances, voltage levels. Now, I will be moving on to the last part of my presentation, which is hopefully to give you the lasting impression of how we are implementing the open access in the KSA. Now, all of my assumptions or opinions here are based on our research. I was lucky to be, in fact, I still am, to be part of a committee that is currently designing for a simple and executable market design for the kingdom. And let me start off with the electricity law implementing regulations in 2005. Because of the licensing feature of this one, the company that I'm working with is National Grid of Saudi Arabia, is given a license to operate, implement, and enforce the Saudi Arabian grid code. The grid code itself is a set of non-discriminatory rules that will be applied to each and every grid user equally in how to access and use the transmission grid. And the creation of this implementing regulation, the Electricity Industry Restructuring Plan, you can see a lot of structural recommendations there regarding the current monopoly. And in 2015, the regulator was able to come up with a CEM design, or the competitive electricity market design. Now, as a conclusion, based on the previous experience, I am laying down the key issues that the Saudi Arabian took in implementing open access to electricity network. I can say that based on from the inception of the KSA electricity law, they have achieved significant milestones in order to implement the open access. Number one is the regulations and policy-making body. So Electricity and Cogeneration Regulatory Authority, based on its licensing power, has a right to regulate all of its licensee to work within the authorized activities so that abuses may not happen. Relevant ministries, I'll cite an example. The Ministry of Energy is established basically to monitor the implementation of the industry developments. Restructuring, there are structural changes in the current monopoly, the Saudi Electricity Company, particularly the creation of principal buyer and the proposed the separation of national grid. Open access framework, we have a grid code that applies to each and every grid user and the KPI mechanism that keeps the operation of the monopolized business under an acceptable standard. Electricity market platform, before this is under development, they came up with a study in 2015 to give an impression that the market should be a pull-type market that operates energy, ancillary services, and capacity markets. So as a conclusion, the Kingdom has initiated numerous steps in implementing open access, and I can say that what they are doing now is to formulate a simple executable initial market so that they can implement a free choice of electricity supply among its consumer. So, thank you for listening.
Thank you, Engineer Ephraim. Indeed, open access provision is a key enabler for trade, not only within a country, but also in cross-border settings with different jurisdictions. Our third speaker is Mr. Adam Terry from UL. In his research, he will draw recommendations for practices for energy assessment of utility-scale hybrid wind-solar facilities. Mr. Terry is an environmental chemist. He has 16 years of experience in the renewable energy industry, specifically the wind, onshore and offshore, solar, hydro, and energy storage fields. His experience stems from site finding, development, pre-construction, acquisition, and operational technical due diligence, as well as turbine supply. Additionally, O&M, asset management, BOP, and civil contracts negotiations, construction and operational monitoring, turbine installation and inspections, and turbine technology reviews. He previously held positions with the developer and several multinational consultancy firms and worked freelance. He has worked on energy projects in 15 countries. He has led and mentored energy teams, including P&L and line management, in which he carried out services for equity, debt providers, developers, owners, and governments, NGOs, and regulatory bodies. He has personally worked on over 5 gigawatts of renewable energy projects and has negotiated supply contracts for more than 1 gigawatt. Please join me welcoming Mr. Terry.
Good morning. Thank you, Mr. Chairman. I'm here today to inform you in the area of renewable energy. Obviously, the Kingdom has very aggressive targets for installing renewable energy, and one of the challenges that faces renewable energy is the fact that it's very intermittent in its nature. Sorry. Thank you. You don't need to see about me. One of those challenges with the intermittency can be mitigated to an extent by the use of multiple technologies. As we've heard from my distinguished colleagues on the panel, the Kingdom has a planned energy mix incorporating wind, solar, and nuclear going forwards. The use of the multiple technologies gives one way of allowing a management of making those technologies more dispatchable for the purposes of the grid. So, some of the advantages that people consider when talking about installing multiple technologies at the same time. And these are kind of split into two different groups. those that are of benefit to the developers, but also those that are of benefit to the grid operators. So from a grid perspective, shared infrastructure facilities mean that it is a cheaper way of deploying technology. You can have more than one installation of renewable energy, sharing infrastructure with another. There's also an understanding that different technologies favor different peaks and troughs in terms of generation, and that aligns in different ways with the demand profile. From a developer perspective, you only have to secure a single site and you can deploy multiple technologies within it. There's a lot of synergies between the development process, so there is a cost saving there. While this presentation focuses primarily on wind and solar as a hybrid, it should be considered that there are multiple different approaches that you can take. And one of the most common or up-and-coming approaches that people are taking in terms of hybrid or tribrid, as it is sometimes taken with, is the use of energy storage in addition to a renewable generation. This presentation is obviously focusing on installing multiple technologies because generally the market is not yet ready for energy storage to provide that solution. However, it is becoming far more common in other markets where the penetration of renewables is high. What to consider when co-locating generation sources? Well, the three topics here provide an iterative process between the different technologies when setting up a site. First of all, you have the resource. That's commonly the driver because, particularly here, there is a prevalence of solar, strong irradiance, while wind is more carefully selected to certain locations in the country. Then you consider how the designs work and interact with each other, the siting within the site, so how you co-locate those technologies. And finally, you consider the energy produced. What is your drivers behind how you install or how you select how much of each technology to use? As you'll see here, it's kind of like a balancing act, a scale. As I say, you can incorporate two or more technologies in one, and the mix of them varies dramatically. There are examples of projects whereby the wind element will be twice the solar element, with potentially a quarter as much again of energy storage, or any mix of the above. For the kingdom, as I say, climate is one of the key drivers. You have an abundance of solar. Therefore, solar is likely to be an easy solution to install. Wind is likely to remain more challenging. However, that can often mean that wind needs to be considered first because of the technical limitations of it. Then there is understanding the cost of it. The different technologies have different costs. They all interact, and it's trying to make the best value for the stakeholders investing in the market, but also for the market as a whole in terms of using it. Maximizing the value of a site. For any developer looking to make a return on investment, the more you can generate from a given area of land, the better. Minimizing the impacts where you have multiple technologies. We'll come on to some slides that discuss how the technologies are interacting with each other within a site and what can be done to minimize those effects. The final 2 points sort of relate to how the output from the site is dealt with, managing it to make sure that you are optimizing it from an owner and developer perspective, but you're also considering the implications from a grid balancing perspective. How much of each technology to use? This slide shows a number of examples whereby there are different mixes of technology. So this has been based around a 75 megawatt installed wind farm with a 40 megawatt solar and assuming a total maximum export, so export cap of 70 megawatts. As you'll see here, obviously strong solar irradiance favors summer and daytime generation, whereas wind generation is typically at its highest in the mornings, in the evenings, and in the cooler months. This is one of the easy ways to consider which technologies you're going to favor within your development. So, as an overview, these 5 items are sort of a step-by-step process that we've learned through a mixture of experience and research in terms of how to size the site. And I'll address each one in turn. This is taken from the approach that wind is a more difficult technology to deploy than solar. Technologically speaking, it is more complex, it is more challenging, there are more factors to consider. So we assume that you will size your wind farm first. So as part of that, we need to consider the area where turbines can be deployed, we need to consider spacing, wake effects, ground conditions, and the variation in the resource over the terrain. So typically we would suggest sizing your wind turbines first. The figure on the right here shows a potential layout with 6 turbines with the associated infrastructure, crane pads and the like, and how they would be typically set out for a southwesterly facing wind resource. Once you've understood what your wind farm turbine layout is going to look like, then we need to consider how the solar is going to fit around that. And this is this is a very high level. This is before we go into the detail of what a solar project would need to look like. This is a very generic setup of maximizing the land area that you have and considering for the design purpose the layout that best suits your longitude and latitude. So the primary angle to the sun. So items to consider here are the angle that you install the panels at, whether you require any tracking, the DC-AC ratio, what the spacing is between turbines, all sorts of things that you would normally consider, and you can consider using any industry standard software to try and develop an optimized solar design. But again, as I say, this is still high level at this stage. Following that, you need to then look at where you're actually going to deploy your theoretical ideal technology. You'll see here that you end up needing to consider the ground conditions, but you also need to consider the wind turbine impacts. And one of the following slides will show one of the concerns that you need to consider for that. But primarily, you need to consider that you have an operating wind farm, or you will have an operating wind farm, and that needs to be maintained and operated throughout the life of the solar park. So you need to maintain access. You need to consider lay down areas for blades and the like, should any replacement work need to be done. And once you've allocated that land, you can then consider any shared infrastructure in terms of roads, electrical infrastructure and then we move on to the shading aspects. So for a site in the Northern Hemisphere, you're typically looking at giving a significant distance in the within a couple of rotor diameters of the turbine location to the north of the turbines. This is where the strongest shadows are cast by the turbines. And so this is an area that you don't generally want to deploy in. Looking at the projects, the two technologies together, you can start to understand the different impacts on each. So your solar park will impact on your wind park. From a simple point of view, it changes the ground cover, which affects the wind resource. It also limits the access to the turbines, so you need to make sure that that's maintained. Ice throw is probably not going to be much of a problem for the kingdom, but there is always health and safety concerns around blade throw and the like, so therefore there's often a sizing difference. What's more important here is the impact of the wind on the solar. The wind turbine casts a shadow. The blades of the turbine cast a shadow. While the shadow of the turbine is relatively easy to model, it moves following the position of the sun. The shading from the spinning rotor has a bigger impact in terms of understanding the impact on the solar installation, and that's because you get a flickering effect, which not only affects the energy production, but it also can potentially impact on the lifetime of the solar asset. The other things to consider are where you can combine share infrastructure, reducing losses on that, managing the export from the combined park, and also any benefits that you can take from having more than one technology and spreading the risk across. So this is one of the slides that gives an idea of how the shadowing shade from the turbines can have an impact on solar. Generally, the shade cast by a turbine forms what we would describe as a butterfly effect. That is, it is strongest to the east and west, with a small component to the north, but that generally is relatively short. So that's why you generally consider avoiding these areas where the shadows are strongest. What you'll notice, though, is that actually the shadows from the turbine are covering the largest area early in the morning, late in the evening, when actually the resource from the solar is at its weakest. So therefore, the actual energy impact from the shading is actually relatively small, as can be seen in the table on the bottom right here. Optimizing the energy production estimates. So you produce energy estimates for both technologies. You do this on an independent basis, but considering the impacts of one technology upon the other. The approaches should always follow typical industry practice, but one of the big challenges that you have to face when carrying out these kind of assessments and understanding how the projects work is in terms of the lifetime of operation. Wind parks have historically considered a 20-year forecast for production, whereas solar farms have considered a 25-year. So when you start to combine the results together, what you need to, as you'll see from this table here, you have a wind result with the 20-year life, and you have a solar result with the 25-year life. Now, wind, we generally ignore the first year because obviously we expect startup issues with the project. But what you'll see from this is that if we look on an hourly basis through the day, you can see the contributions from each technology. And what that does is it reduces the peaks and troughs in generation. It smooths the generation profile, which makes the combined output of the park more attractive from a grid management perspective compared to either technology on an individual basis. As part of this process, you're looking at combining both energy, but also the uncertainties and losses. Having two technologies gives you an opportunity to reduce the uncertainty, because there is a widely proven concept that by sharing across multiple technologies, you're reducing uncertainty because the two technologies are quite complementary. And therefore, you're generating additional value for the owner or developer of the project. This chart here is basically just showing how those periods during the day when we'd expect a combined output from the two parks as opposed to a single output from one of the technologies. Looking at how we combine that uncertainty of the two different technologies, what we see is that some of the uncertainties reduce each other because, for example, wind has a fairly standard 10-year forecast, whereas solar has a consistent degradation applied to it over the lifetime. So the two do not necessarily go together. So it provides a varied effect on the probabilities of exceedance. But it is still possible to calculate these for the typical financing terms of 10, 20, and even 25 years. This chart is basically showing what we call the portfolio benefit effect, and that is where the two technologies are providing benefits to each other. So, for example, you would forecast any outages on your wind plant during periods of low wind. Periods of low wind often tie in with periods of clear sky, wherefore the generation from solar is at its highest. So they're mutually beneficial there. One of the things that we then start to consider is when deploying this technology is some of the impacts that you need to consider both from a developer and a grid perspective. As I mentioned, obviously we assume that the first year output from a wind farm is lower and increases thereafter as operational performance improves. As I've said, solar degradation, how that works across between the first year and the average over life, and the different forecast periods for the energy production estimates. From a deployment perspective, what we're recommending and what we're seeing people do when they're deploying multiple technologies is actually they're producing 2 independent engineering reports to give lenders comfort on a traditional financing basis, but then a specialized report which addresses the combined effects of the 2 projects. So this is talking about how the 2 energy production estimates the 2 projects are impacting on each other to create the hybrid loss factors, also the impacts on shared infrastructure in terms of construction schedule and delay, the relationship between the technologies. Hybrid projects are generally at their easiest to deploy if they are deployed simultaneously, rather than adding a second generation source or storage source to an existing infrastructure. Also understanding how O&M is forecast, how it's planned. As I say, you want to schedule your wind outages at low wind when there is high solar to take up some of the slack in the production. And finally, as part of that, you also want to consider the sort of electrical safety and reliability of the system. So this goes back to considering how the flicker from the turbine blades impacts on the solar panels' performance. And that is it, really. I mean, that's sort of our approach for trying to understand how the 2 technologies work, how they can be used to sort of de-risk and provide a less intermittent output to the grid, which obviously means that it's easier to deploy larger quantities into the market. Thank you.
Thank you very much, Mr. Terry, for this presentation. Our 4th speaker is Engineer Rami Kalantan. He's going to present his work on developing a planning model that is developed to assess the future of energy demand, utility costs, and revenues in Saudi Arabia. His work is part of his master's degree of sustainable energy at KFUPM, along with his colleague, Engineer Muhammad Al-Mudhi. Engineer Rami graduated from KFUPM with a master's degree of engineering in sustainable energy in 2019, after obtaining a bachelor's degree of science in electrical engineering in 2016. He joined Jubail Energy Services Company, Taqa subsidiary, in 2017 and NOMAC in 2019 as a planning engineer overseeing the short, mid, and long-term maintenance requirements for the plant and monitoring its performance and reliability aspects. Please join me welcoming Engineer Rami.
Thank you very much, Dr. Turki, for the introduction. Assalamu alaikum. Good morning, everyone. This project was done during the master program at KFUPM in the Sustainable Energy Master Program. It was done with Muhammad Al-Mudhi, my colleague, who was supposed to present this presentation, but I am representing him here, and myself and Dr. Ali Al-Awami. The project examined many topics related to the electricity industry in Saudi Arabia. In this presentation, we would present part of the research and look at the main commodity of the industry. The content of the presentation will be as follows. We are going to have a brief introduction about the electricity industry. Following that, we will going to present the energy demand model. And finally, we are going to talk briefly about some contributed sectors, including mainly the transportation sector. The industry has experienced a continuous growth in customer generation capacities and networks. In simple, dynamic changes and development has always shaped the industry, especially in the recent years. So, the industry since mid of 90s has been shaped by continuous changes and events that help to get it where we are today. So, we are speaking about a business and industry of 300 terawatt hour today. So, where would it be in future? What will be the future energy demand? What are the dynamic variables? And where the growth trends are going to be? To have an idea about that, a proposed energy demand model prepared in this project. We needed to create an energy demand model to quantify the growth based on certain factors. Those factors are simply dynamic and driven by the consumers and the growth of the customers and their consumption. So, we are speaking here about the number of customers and the average of energy consumption. These variables have been divided on the 4 regional areas of the kingdom: east, west, north, and south, where historical data are used for it as an input. The model, with some details, linked many variables in the industry and many sectors, and we highlighted the transportation sector. As well, specifically as the electrification of this sector will add a huge contribution to the demand. Now, speaking about the first variable, this chart shows the growth in number of consumers in different operating areas in KSA, highlighted, of course, with different colors. For the past year, for the historical past years, as shown, and the created forecast of these customers has been used as an input for our model. We made sure to roll out any overgrowth or exponential growth in this model to keep the output as realistic as possible. Similar with the growth of number of customers, this chart shows the historical changes of the consumption per average customer in each operating area where the future trends shows. So, speaking about our main topic here, which is the energy demand. From 300 terawatt energy demand as of today, it is expected to go to 500 terawatt hour by 2030. However, considering the efficiency programs and the new technologies and the improvement also of the new technologies, this will lower the consumption, so would have a more realistic demand, expected to be around 400 terawatt hour by 2030, which is shown here in the gray. To have a different view, here is the expected change in the average of consumer by 2030 as well, which is shown in the right side. So, of course, we are going to have some challenges. One of that will be the expected peak load growth rate. It is expected to continue in fluctuation, but at a much lower rate, which is expected to be around only 3.9%. Also, speaking about the generation shares as well, the game will be also changed in future. The key players of the game also and their share will be changed, of course, as well in the future. Of course, in future, speaking about more demand, we require, of course, more transmission and distribution network expansion. So if we imagine that adding only 100,000 customers to the network, you can see how much of transmission capacities we have to add, how much distribution capacities we have to add, and so on. So we want to reach that. It will require, for sure, a much more huge investment to accomplish that in the future as well. There are many sectors which is developing very fast, and some of them, of course, will mainly affect the demand. We specifically choose the transportation sector, as the electrification of the transportation sector is a new trend and might grow in future. We are having many projects commissioned and under commission, and we currently expect to add around 9 terawatt hour by 2030. At some point of the study, we had to examine the consumer behavior, and for that, we estimate the average annual consumption and the annual cost to estimate the trends. We found out that the consumption decreased as the cost increased. This is for the residential, and the similar behavior was shown also in the commercial, government, and industrial. So, to conclude this presentation, the electricity industry are expected to grow in future. The energy market expected to be around 400 terawatt hour by 2030. Customer may grow up to 15 million or more by 2030, which will require, of course, more investment in transmission and distribution. The electrification of transportation sector will contribute very mainly with a huge amount as well to the total demand. The demand peak will grow at lower rate, and the customer sector behaviors, of course, are changing. And finally, the generation sector trends and the shares and the players of this game are going to change as well in future. That's it. Thank you so much, and I really appreciate KFUPM for supporting us in this project totally. Thank you so much.
Thank you, Engineer Rami. I think your research is very important in setting the tone for the development of electricity sector in Saudi Arabia. These were very information-rich presentations. I would like to thank all speakers. And now, in the next few minutes, I would like to open the floor to receive questions from the audience. Please, before you ask your question, state your name, your affiliation, and to whom you address the question. Can we have the microphone in the first row?
Bismillah ar-Rahman ar-Rahim. Khalid al-Sultan, Chairman of SCC. Thank you very much for the presentation. I think we need this analysis, but there are quite few assumptions that I haven't seen them in the analysis. One of them is the mega projects like NEOM, like other major projects that are going to be done in Al-Giddiya and Al-Ula. These are important factors. Second, what was the basis for selecting the 3.8% growth in the peak? I mean, definitely for the past 2 years, in 18, we saw little drop in the peak. In 19, which happens this year, in 2nd of September, the first day of the school, very little increase over past year. This growth will definitely be a function of the economic growth in the kingdom and the demography, but there are more in-depth analysis that I wish that you get into, and I would recommend that you and your colleagues and your advisor get into, because in SEC we don't agree with the 3.8 model. I know that 3.8% is subscribed to by maybe the ministry, but what was the basis for selecting the 3.8? And then what was the basis for selecting the growth in the customers. The customer growth was 500,000 the last 2 years was 300 or something. The population growth in the kingdom is going down from 3.2 to now 1.8, and we expect it to be down in the future. So these are quite important assumptions that you have not covered, and I'm sure that you have discussed them with the group. So
thank you so much, Dr. Khalid. Regarding the first question about the Giga projects, yes, I agree with you. Mainly we have considered now the well-known projects in the transportation sectors, which is well-known and easy to estimate it separately as well. Regarding the Giga projects, we consider it as it will be mainly contributed to the main demand. Our model can be updated year after year. The data of the model can be updated year after year. So if it is did not consider specifically the Giga project, it will be considered mainly at the end for the total demand. Regarding the second question, our aim at the beginning was to show that the fluctuation of the growth percentage will not be that much big fluctuation. We were aiming to reach to a conclusion that the fluctuation will be yes available again, but at much lower percentage comparing to the previous. However, all of these data are going to be updated yearly and yearly, so the total conclusion and the total result will be more accurate year by year up to 2030.
Last thing for just your benefit and the benefit of the business. I mean, this model, what you presented, subscribe to what SEC has been doing since inception, is chasing the demand, assuming that the demand is uncontrollable and it just impacts the supply. What we're trying to do now, and definitely with the introduction of smart meter, we will be able to manage the demand rather than the supply, which SEC has been doing in the past. And one of the ideas is to shave up the peak. So, you know that the peak is 62, while in some days in winter, the consumption is only about 27. The energy consumed is only 26, 27. So these are the factors that you need to, if you revisit the model, you need to take into account. So, thank you.
Thank you, Your Excellency, for these insights. We can have the question in the first row.
Thank you very much indeed. My name is Mohammed Adjour from King Abdulaziz University. Thank you very much indeed for your excellent presentations. My question is, what is special about Saudi Arabia with regard to the legal aspect? I mean, do we want to reinvent the wheel? I mean, many other countries started where we are starting now, and they have already well-established legal framework. So what's special about Saudi Arabia?
I can take part of that question. So when you're looking at the way the renewable is developing and the amount of the actor that you would need in the market, today the way the law has been designed is, let's say, it for a system with mainly, can you hear me okay? Yeah, a system with mainly classical generation, and with the introduction of renewable, you need new actors to be able to play on the market. For those new actors, new laws has to be implemented to facilitate the investment for those actors and to provide security for them to invest on those new type of generation or new types of support that the system operator may require.
Any question?
Assalamu alaikum. I'm Dr. Amjad from King Fahd University. In continuity of Dr. Khalid's comments, I just want to give some comments that I'm also doing the same work, and I used 5% increase in electrical growth. So as per my study, I think in 2018, 62 gigawatt was the peak demand and 79 gigawatt was the generation. And conventional power generation system, which is in the pipeline for 2018 and 19, is 19.4 gigawatt. And keeping in view of Vision 2030, solar power plant generation system by 2023, overall kingdom's power generation system will be 132 gigawatt. And by adding the 5% increase per annum, kingdom's power demand will be round about 95, 96 gigawatt. It means by 2023, we will already have 40 gigawatt of surplus power. And again, we are going to add 58 gigawatt of the renewable energy. And question raised here, are we really ready to absorb, or the national grid transmission system ready to opt this surplus power system in their transmission system, and where we will use this one? By 2023, if we are talking not 2030, by 2023, we have already 40 gigawatt of the surplus power. Where we will consume this power? Old power plants. If we'll add the solar photovoltaic, that time we need a standby conventional power system at night time, at evening time. Then again, we will have a very big cost or the financial burden of the national grid system. Yes, this is the issue. So this one, thank you.
Okay, so I will take the advantage of being the moderator and ask a question to our second speaker, Mr. Afrim. I think you very well provided a background about the open access in Saudi Arabia as well as in different countries. I would like to see your opinion on how to reflect that in the GCC country context. Now, there are efforts to intensify the trade, the cross-border trade, and the open access is one of the drivers for that. So what do you think, in your opinion, that we need to do in order to move forward with the cross-border trade among GCC states?
Okay. One of the key elements of open access is that all mechanisms for open access has already been established. National Grid, by its transmission license, is allowed to secure an arrangement with other transmission companies when it comes to like inter-area interchange. Now, I'm not privy of any interconnection agreement, but the point is that since we are seeing a lot of manifestations about open access, say for example the grid code itself, and the transmission license we have is we are designed to do such things. It's quite a challenge for regulations to do such, and I would say that the company by its current mechanisms is bound to do the interconnections like that.
Thank you. I believe we have come to the end of the session. Big thanks to the presenters for the great contribution. I would like also to thank the audience. And if you can join me thanking the speakers for their efforts.
شكرا لك أيضا دكتور تركي، وأسأل الآن أطلب من معالي الدكتور خالد بن صالح السلطان رئيس مدينة الملك عبد الله للطاقة الذرية والمتجددة، أطلب منه تكريم المشاركين في هذه الجلسة. تفضل دكتور. البداية مع مدير هذه الجلسة الدكتور تركي العقيل. السيد أسامة بدارة، وسيد فريم نوفيناريو، السيد آدم تيري، والمهندس رامي كلنتر. وكان لدينا أيضا مشاركة لافتة من سيدة ريتا ألن، فنرحب أيضا بالسيدة ريتا ألن. Please to the stage. دكتور تفضل. شكرا معاليك وشكرا لجميع المشاركين في هذه الجلسة. السادة الحضور، موعدنا يتجدد على رأس الساعة في الجلسة السادسة. كونوا على الموعد وشكرا مجددا لحضوركم.
Ladies and gentlemen, we're having a coffee break for 30 minutes. Ladies and gentlemen, Ladies and gentlemen, welcome to the 6th session titled Flexibility and Grid Resilience, chaired by Engineer Raed Abdurrahman Al-Harfi, Manager of Extra High Voltage Network Planning, SEC. First paper, The Great DR Project, Controlling the Load at the Grid Edge, presented by Mark Lacroix, Emekre. Second paper, The Future of Saudi Arabia Grid, exploring large-scale renewable integration scenarios, presented by Al-Assan Naddour, Saudi Aramco. Third paper, using IEEE standard 738 to increase rating of overhead transmission line, presented by Jamil Muhammad, Egyptian Electricity Transmission Company. Fourth paper, overcoming the challenges of sustainable energy integration, presented by Thames Spearing, Lucy Electric. Fifth paper, introduction of auto reclosures in distribution network to improve the KPI's performance, presented by Nasser Al-Hakami, National Grid. Sixth paper, a novel method of using BESS for controlling system frequency and area control error through AGC integration in Abu Dhabi Power Network, presented by Ihtishamuddin Iftikharuddin, Abu Dhabi Transmission and Dispatch Company.
Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, you are welcome in the session number 6, titled Flexibility and Grid Resilience. I will save the time for our experts here to go deep in their papers. We'll go deep to know how to increase the resilience of the grid to be by using the existing asset, increasing, for example, the rating of transmission line, updating the operation mode, or even how we deal with the challenges with the renewable, the integration of the renewable. So we will start with the first paper, the Great DR Project, Controlling the Load at the Grid Edge, will be presented by Mr. Mark Lacroix from Canada. He has 40 years experience at energy sector, at automation field. He is working now at Emekre. Yes, welcome. Please welcome with me Mr. Lacroix. Okay.
Good morning, everyone. So I wrote this paper with Raed Abdullah from Ottawa. Ottawa is a small utility. In fact, it's the distribution company that distributes the energy in the Ottawa region. Ottawa is the capital of Canada. Myself, I work at Emekre. Emekre is a company that helped the company in the banking and financial sector for the last 15 years to succeed their digital transformation, and now we have adapted our solution for the energy sector. So today I will present you first we'll talk about the industry transformation and what are the challenges of the industry, and then I will describe the two phases of MyGen. The phase 1 is now finished, is now completed, and the second phase will start next year. We'll talk about the loyalty management, which is a key part of the second of MyGen phase 2, and we'll talk about the new economical model we can have with the new approach. So the industry sector will face many changes during the next year. And here we see it was published by the World Economic Forum that the three main changes in the industry will be the digitalization, the decentralization, and the electrification. So for the decentralization, we mean all the development at the edge of the system, so close to the customer, to the residential customer. The digitalization, it's all the installation of the smart meter. But also we should not forget that also the customer, they have their own digital transformation at the same time. And the electrification, so yes, it's coming. The electric vehicle will be present in our life. So talking about the transformation at the edge, what we mean by the edge, it's all the devices installed in the intelligent home, the smart appliances, the home generation, the storage inside home, and all these new technologies will be more and more popular. You see in the graphic below, this was also in the World Economic Forum report. The last curve in red is what is expected as the market grow in the edge technologies. So we see that the tipping point is planned to be in around 2020, 2021. And after that, we'll see an exponential augmentation of the transformation, the edge technologies. The transformation at the edge will have a big impact on the system, not only on the distribution system, but also on the power system. So here we have an example that these curves come from the Ottawa system. Just to mention, this is a North American type of distribution system. So you have a substation with long distribution lines that distribute the energy to customers, and with a lot of transformer attached to these feeders. So we see here that on the feeder with a lot of renewable installed in this feeder, that the peak is at 11 p.m. And on the feeder, the peak is at 8 p.m., while in the substation, it's at around 3:30 p.m. And on the transmission system, the peak is at 6 p.m. So you see that now there's a lot of change that is brought by all these new technologies at the edge of the system. The impact of electric vehicle will be great. On average, electric vehicle requires 3,000 kilowatt hour per year. So we need to build a new electrical market, because there's a lot of challenge, but also all these challenges bring some opportunities to the industry. So we plan that in the next decade, the electric system will change more than the last 50 years. So the new business should be developed to take into account the opportunities, but more important, the new business model should be based on the customer. So it should be a customer-centric solution. So the other thing, and another key point, is that it's important for the company to create the flexibility. I mean by flexibility, the system can adapt to any change of the system. So how many cars there will be in 10 years from now and 20 years from now, we don't know, but we need flexibility. So with this in mind, Hydro Ottawa launched the MyGen project. On the first phase, the MyGen project objective was to manage the energy at the distribution transformer level. So here we see on the left the main element of the MyGen with the HAMNC. It's the Home Energy Management System Controller that communicate with the TA, the transformer agent. And the transformer agent look at the overload of the transformer, and if no overload condition exists, it will communicate with the different HEMS connected to this transformer to reduce the load. And we see some results here with this negotiation. In the 10 iteration, the demand has been reduced by 22% without any other measure of a performance. So it gets very good result. So based on the result of phase 1, we will start phase 2. And the main element of phase 2 is to develop the customer relationship, because it's really important to create a good relationship between the utility and the customer. And also we want to empower the customer. So the idea also is to support in the future the transactive energy, improve the energy forecast accuracy, because in the future the behavior of the customer will have huge impact on the load, and the load forecast will be affected by this behavior. So we see here a high-level architecture where we have here at the bottom the different devices we can find in an intelligent home. But we have the domestic generation, the energy storage, and the smart appliances. All the information from these devices feed a big data analysis platform that use all this information to detect the behavior of the customer, and with enough data to be able to detect or to predict the future behavior of the customer. And we have the loyalty program that takes the information from the data analysis platform, and that allows the utility to reward the customer who participate in the market. So that's the new idea we bring in this project, is that now we'll reward the customer instead of punish the customer who use more energy during the peak period. Just to give some example, what can be the loyalty management. So here we have different campaigns. So each campaign is create for an event. Like say there is a peak coming in the next day, so we create a program that will cover this period, and we have a kind of engagement from the customer to reduce their energy. And in exchange, we'll give them loyalty points. But also, different other programs can be used to organize forecasts, or to organize teaching program with the customer. And each time they go to a learning session, they will have new loyalty points. Just a few words on the big data analysis. So the idea is to take information from different sources, like here the social media, satellite images, the HMS, and to take all this information and to retrieve very, very interesting information for the system operator, like the load forecast, customer behavior, security alert. An example here, what we can do with the data analysis platform and the loyalty program. Here we have the curve, the expected curve of the load demand, and we see in red the expected curve with the loyalty program. So we can have some interaction with the data analysis platform. We change the number of points we give to the customer, and we can see that the red curve will change with the number, depending on the number of points. A few words on the customer empowerment. So there is 3 phases. The first phase is to know the customer, to classify the customer in different categories, in different clusters, and after that to engage him. So when you know the customer, you have grouped your customer, you can have specific messages for each cluster. And at the end, you can influence your customer. You can have a special program for your champion. And you can also change future behavior of the customer, influence its behavior. And what we talk when you think about the economical model bring by this new approach, we see on the left in orange all the customer energy assets that are managed by this new approach, and on the right all the value stream created for the utility. So we see that we have the intelligent appliances that allows the reduction of kilowatt, the energy storage in kilowatts, and so on and so forth. And on the value stream, we see that the utility can be on the carbon market because it reduces the carbon use, and also it can reduce the price of generation, total generation. So it's a very new business model we propose. So in summary, the utilities will benefit in many ways from the load control at the grid edge. It will enable the utility to defer some major investments, support new ancillary services, increase overall resiliency, optimize the future investments, and a new business model should be customer-centric, customers that become active participants in the system. In fact, the customer become some economical partners of the utility. And finally, create flexibility to support new business opportunity. Thank you.
Thank you, Mr. Mark. We will allow for just one question because you spend a long time, Mr. Mark. Any questions? So we will go to next presentation. The technical paper will be presented by Al-Asna Nador, 20 years experience in power system field. He's working now with Saudi Aramco Power System Planning Department. Please welcome with me, Mr. Nador.
Do you hear me? Yeah. Thank you. Assalamu alaikum. Good afternoon. It's really a pleasure to join you today to discuss the challenge that our industry is facing. First, let me thank the co-author of this paper, Yang Ho, here in the room today, and my colleague Santiago de la Ranaga. Today, my talk will be around integrating. I will show you some modeling large-scale renewable into the KSA system. So let's start with a best practice example, Germany. In 2000, they passed the feed tariff law. They had 6 gigawatts of renewable, 5% roughly of the energy mix. In 2018, they reached 37% of the energy mix. So roughly 95 gigawatts of renewable. So as you can see, Germany experienced roughly 20 years of technical, regulatory, and policy challenge related to renewable. Now, one very particular date and very important date, 2015. 2015, they had a solar eclipse, and suddenly, 8:30 a.m., they lost 6 gigawatts of renewable. 1 hour later, 1 hour and a half later, they have a surge of 13 gigawatts. So just imagine the stress on the system. You lose 6 gigawatts, and suddenly 1 hour after, you have 13 gigawatts, and you need to absorb these 13 gigawatts suddenly. This is exactly the type of challenge that you face when you have a lot of renewable. Now, the country, the kingdom is really moving. The kingdom has very, very ambitious plan around renewable. And the challenge there is a lot of challenge associated to put 60 gigawatts roughly by 2030. The main driver, to value the resource of the country, gas and renewable resources, preserve oil for more added value, typically chemical and export, but also decarbonize the energy sector, and mostly decarbonize utility sector and the transportation. So now, how to get there? And this is the most important question. We perform exactly these studies, this study on renewable, first to understand the challenge, to quantify the challenge, and then to propose solution. Propose solution to our management, but also to the kingdom, to all the stakeholders that are working on these issues. So today I will talk briefly about the system itself, the kingdom system. Where are we and where are we going? So I will talk about load, supply, challenge related to nuclear, to renewable, and I will briefly talk about the Dirk curve. And then I will show some results from the modeling. So as you know, the KSA system is really in a very profound mutations. And one of the big challenges in the kingdom is really the seasonality and variability of the load. Variability by season, but also on a daily basis. And this is mostly due to the weather. Now, today, this year, we reached 62 roughly of peak. The peak was roughly around 62 gigawatt. But just imagine, you have a load in the summer around 60 gig, and during the winter, you have 30 gig. So just imagine this stretch that you put on the system. How many plants you need, additional plant, to meet your peak. On the supply side, we have roughly 90 gigawatt, 16 gigawatt from the desal, 7 to 8 gigawatt from the CHP, and the rest is conventional plant, steam, simple cycle, and combined cycle. Now, as you can see, your inflexible generation is almost 25% of your capacity. Inflexible means that these today you cannot ramp them up and down very easily. Now, all this effort done by the different stakeholders, government, utilities, on the supply and on the load side, we have noticed a very good move, actually, but a very good change in terms of fuel mix. So typically in 2013, the mix, gas was around 47% of the mix. By 2018, we reached 55% by putting much more efficient plant on the ground and by making gas available to this efficient plant. So now, where are we going? The future is almost by 2030, 70% of gas. And now you can see here that this 13% is the amount of liquid that you will displace if you put this 60 gigawatt of renewable on the ground. So again, with all this effort, load, supply, and also on the fuel optimization, now the fuel efficiency has improved a lot. So we reached 39% by 2018, And the goal is to reach 45% by 2030. Now, if you include in this piece the renewable portion, you will reach much more than 50%. I will go really briefly through these challenges. Typical challenges related to renewable in the kingdom: market design and reform. We need to do some progress, institutional framework and regulation, and of course, energy subsidies and tariff. So this is the curve of the kingdom. This is a typical day in the winter where you have really the most related to renewable. You have a lot of stress on the system. So here you have the load in dark blue, and you have now what we call the net load. It's the difference between your load and your renewable penetration. Okay, so let's just take an example, the light blue. The light blue is the net load at 30 gigawatts. As you can see, the morning when people woke up the morning, you can see that the load is increasing, and go to work, the load is slightly increasing, reaching the peak here. Now, at the same time, the sun is rising. The sun is rising, you have a lot of renewable. In 2 hours, just 2 hours, you need your conventional resources, you need to remove the amount of megawatt, 30 megawatt here, 30 gigawatt provided by your conventional resources. So just imagine the stress on the system. You suddenly have to remove 30 megawatt from the system. And then a couple of hours later, you have to ramp up your unit to meet the peak. Okay? This is exactly the type of challenge that the system faces when you have a lot of renewable. So now I will move to the modeling. So this morning, my colleague Mohamed Nasser presented you some results that he got from the long term. So typically here we use Plexus, a typical integrated energy model optimizer. So for long term, the objective function is to optimize, minimize capital costs, operating costs, retirement costs, and environmental costs. So we run the long term until 2035, and then we pick 2 years where we have exactly the scenarios that we want in terms of renewable, 27 and 59 gigawatt. And then we zoom on these 2 years, so we run these 2 years on an hourly basis to get the dispatch. So first set of results. This is a scenario at 27. At the bottom, you have your inflexible generation, desal and CHP. And then you have your combined cycle, following the fluctuation of your net load. This is exactly, if you want, a duplication of your duck curve, but this is a 2 weeks window. As you can see, you have some stress on the system. So now the outliers, the red outliers, this is the excess of energy that your system cannot absorb. This is what we call curtailment. Okay? Typically in this scenario, we have 5%, 27 gigawatt, we have 5% of curtailment. So 5% of curtailment, the system should be able to manage this amount of curtailment by minimal change into operation. Second scenario, 59 gigawatt. So here, we have much more inflexible generation because we have 2 nuclear plants online by 2029 and 2030. But we have a lot of renewable. So the combination of a lot of renewable plus more inflexible generation, we reach 25% of curtailment. And you can see this is roughly over the year now. If you extend it to the year, this is roughly $35 million loss. So how to fix that? Because we need to fix that. We need to be able to capture this amount of renewable. Flexibility. And the key word is flexibility. And a couple of colleagues talk about flexibility today. So I will go very quickly because I think I'm running out of time. You can decline flexibility by really 3 layers. First, institutional, role and responsibilities of the different authorities, government, and regulation. Second, technical rules and economic incentive. You need standards. You need to put the standards. And again, we don't have to reinvent the wheel. There is a lot of very good standards on renewable. We need to know exactly how to apply these standards to the kingdom. Adequate target and incentive. And this is where we need really also to push for renewable. If really, we want to reach this 60 gigawatt, we need to put the legal and institutional framework that can help really to put much more renewable on the ground. Flexibility market, and we'll see later. These plants that are ramping up and down, you need to be able to compensate them. If you want them to ramp down because you want to absorb more renewable, you need to be able to compensate them. You need to be able to put a market where they can make money and recover their costs. And last but not least, one of the most important, it's really the hardware. And the hardware, you have the generation. So you need to be able, first, to allow your renewable to provide services. Now, your conventional plant, you need to be able to give them incentive, this generation, so you can retrofit the plant, you can increase the ramping of this old plant, you can also improve ramp up and down capabilities. Second, transmission grid. You need to increase your transmission capabilities, your interregional capabilities, but also your capabilities, your export capabilities with neighboring countries. So let's see an example of flexibility. So here, typically, what we did, we tried to model a little bit some flexibility. So we put a soft constraint on the inflexible generation. And as you can see, what the model is doing, it's tapping on the first resource, the less expensive, if you want, resource, that he can ramp up and down. And here it's an example, but here it's the CHP. So typically when we run this case, we moved from 25% to 13%, 18% of curtailment. So typically, we got 7% of, if you want, we absorbed 7% of the losses. So you can see that you need much more flexibility than that. This is not enough. And I will conclude with the type of solutions that you need to improve your flexibility. So first one is, of course, at the planning stage, you need to optimize your renewable plan, renewable mix, the mix between, and by region, the mix between wind and solar. Second, the spatial and geographic diversity also, it's a very important point. You need to tap in the demand resources. And for that, you need tariff reform. I mean, at the same tariff, it's very difficult to tap into the demand responses. Second, you need to allow some aggregator to play in the market. So you need a strong market and a sustainable market. Again, you need to increase the ramping capabilities of your generation fleet, especially the conventional one. And you need some solutions, some more flexibility on the transmission side. But last but not least, very important, you need to tap into the advanced storage solution. Batteries, EVs, thermal storage, fuel storage, hydrogen. These solutions are available today on the market, and we can learn a lot from all these countries that already have put a lot of renewable on the ground. So I will conclude my speech with this. I just want to thank again my co-author, and thank you so much.
Thank you, Mr. Nudur. Yes, we agree that we need to consider all the sides of increasing the resilience, not only in the grid, even on the demand or supply side. If you have questions, we can just allow one. You can introduce yourself, please.
Hi, Michael Burke from Saudi Aramco. Very interesting presentation, Alassane. Just one question on the dispatch cases. With, you were showing that there was some curtailment necessary. We still had a lot of CCGT in the stack. Why did we not two-shift that or shut that down? Is it a function of the slow ramping of those units as it stands and the not being capable to shut down and start up very quickly?
I'm sorry, Mike. Can you repeat the question? I didn't get really.
Yeah. So you showed us several.
If I'm correct, your question is about the fluctuation on the CCs?
Yeah, just wondering why we're showing curtailment, but at the same time we still have a lot of CCGT plant running. So why do we not shut that down? Is it because those plants are incapable of shutting down and ramping up quickly enough? Is that the reason?
Typically, it's one of the reasons. The most flexible units that you have currently, it's simple cycle. It's not your combined cycle. So your combined cycles still have a longer ramp rate. So it's typically because they are not fast enough to catch up the different fluctuation.
Okay, so that's where we need market design to come in.
Yeah, exactly. Now, part of the solution is really to put on the ground. So and this is part of the regulation. You can put some subsidies, incentive to retire the plant not flexible and to change them with very flexible new frame and very flexible frames. There is a couple of new frame on the market, very flexible. Okay, and this is, I think, part of the solution. And maybe there is somebody from SEC in the audience. I'm sure they're looking for this type of solution.
It seems that we have questions from Mr. Mansour Al-Gahtani.
Thank you. You introduced the demand response as one of the solutions. How much you estimated the contribution of the demand response at the high scenario? You got the question? All right, thank you.
I'm sorry. And here I 100% agree that demand response is one of the solutions that we need to model here. And this is one probably of the next step. It's to add the demand response into the modeling, but also to add storage also. We're thinking about adding some batteries. So typically in these scenarios that I show today, we don't have demand response. It's not modeled. It's not modeled. But definitely we need to tap into this resource if we want really to have a more flexible system. And again, if flexibility is a concept, it's not just, so it's a concept through all the value chain, from generation to the end user. if we are able, the different stakeholders, to sit together, to brainstorm, to learn from the other country, I mean, the 60 gigawatt is not, it's a challenge, but it's a challenge that the kingdom can overcome.
Last questions from Dr. here.
Thank you for the nice presentation. A quick question about this 59 gigawatt is very significant amount compared to the Saudi Arabia generation. And this will impact the inertia of the network, of the system. So from stability point of view, injecting this 59 gigawatt in our network, how is the impact will be on the grid stability, especially that we are going now to reduce the inertia significantly?
I'm sorry. So this 59 gigawatt, I totally agree, will impact the inertia of the system. But also there is some solution for that. Already, today, you can get some synthetic, what they call synthetic inertia from your renewable. So your renewable can provide this type of services. This is one. Second, we didn't model here inertia because this type of modeling cannot capture inertia. When you do a full integration, a renewable integration study, you need to have a kind of loop with modeling type PSSE, PSLF, so you can understand exactly the impact of inertia. We didn't do that in this modeling because it was more a planning from the generation side point of view. But definitely we need also to look into that. But I think, again, this is more I think there is a group in the utility today, in SEC probably, doing this type of very deep dive work that includes the grid, I mean, on the model, on KSA, on the kingdom, I'm sorry.
Yeah, if you allow me, Mr. Nadur, yes, SEC is working on stability analysis. Of course, we will end up with increase the integration between the areas. Also, converting what you call the small units in different areas into synchronous condensers is another option. So there are many options. Yes, we modeled everything. We modeled the renewable. We modeled network up to 2040. So we will end up with many ideas or projects that will increase the inertia. Thank you all. We spent a long time with Mr. Nadur on this paper. We'll go to the next technical paper. Will be presented by Mr. Jamil Muhammad from Egyptian Electricity Transmission Company with 20 years experience at automation, at energy central control. The master degree in automation control, will present the paper titled Using the IEEE Standard 738 to Increase the Rating of the Overhead. Please welcome Mr. Jamil.
Assalamu alaikum. Good afternoon, everybody. Thanks, Chairman. My technical paper under naming using IEEE standard 738 to increase rating of overhead transmission line. We can start. Yes. Background and problem definition. A smart grid is an electrical network uses modern technology to control transmission of electricity. A line monitoring and control device can maximize network utilization to increase network efficiency and reliability. and solve the network congestion that might occur. The electricity network context congestion occur where demand for power transmission exceeds capability of the transmission network. Yes. Sometimes congestion happens during the maintenance hour or during failure of any part of the network, maybe transformer, maybe any circuit. The proposal will concern with the possibility of increasing the design capacity of the electricity overhead transmission line without causing any hot point or overcurrent or melting. This is supposed to by taking advantage of the measurement of temperature and wind speed affecting the transmission line and calculating the dynamic line rating based on the measurement. Dynamic line rating system is kind of smart system that could be implemented in the smart grid. Our research objective to evaluate how using the large system can relieve the congestion. We implemented a thermal model of IEEE standard and studied the congestion on the certain network. The result of implementation of our program on real congestion cases proved the feasibility of using it. Therefore, we can say that in order to resolve the problem of congestion, on the following solution should be done. The first solution, increase generation in the area of congestion. The second solution, provide line or cables that reduce congestion. The third solution, add device and exciting transmission line and provide load on them. The first two solutions cost a lot of money and need more time. But third solution, we solve the problem of congestion in short time and less expensive. DLR technology is inexpensive to install and operationally flexible. Most of the time, transmission line have more available real-time capacity and a greater degree of flexibility than their static line rating. When employed, the large system help a transmission owner to absorb and take advantage of this capacity. The transfer capability of overhead power line are often limited by the critical power line temperature that depend on the magnitude of the transferred current and the ambient condition. The algorithm has been tested using typical atmosphere condition in Iceland along with the overhead line real design. We are restricted with the line temperature that shouldn't exceed the maximum design temperature to avoid hot point or melting. The thermal equilibrium equation of conductor summarized into heat gain sources, heat gain from sun and heat gain from the current, and two heat losses, convention heat losses and radiation heat losses. This equation can be used from my program. The thermal equilibrium model is used to calculate amount of heat gain and heat losses on the line. And wind surrounding the line is one of the reasons of heat losses and why the sun is source of heat gain. Using weather station near to the line measure the wind speed and sun radiation help in calculation of heat losses and gain. Some DLR system communicate with utility energy management system through the SCADA. The SCADA system with the measurement and calculated information. Dynamic line rating are determined by understanding the thermal relationship between the conductor and the power flow and the ambient condition. Implementation of the DLR program The implementation is performed using Oracle database. The program is designed in 1-3 base that contain the main parameter of conductor and displays the measurement, conductor temperature, ambient temperature, wind speed, wind direction, and the program calculates resistance of conductor at temperature, and the heat gain from sun, and the convection heat losses, and radiation heat losses, and they calculated the dynamic line rating through the conductor. And make validation of calculation program when I comparison between value data from the reference and from the calculation program, the maximum percentage of calculation error of our DLR calculation program does not exceed 2%. The goal of any DLR is to measure specific parameter to calculate the dynamic line rating and capacity margin. This goal is accomplished by measuring key operating conditions that affect the line capacity in real time. The operating conditions are weather conditions such as ambient temperature, solar radiation, wind speed, wind direction, and some DLR devices use point sensors that gather information at only a specific location in the transmission line. From experimental result, we can take two cases, FDOMRA network, my Egyptian, network 1500 kV, and the network 220 kV. The graph calculate DLR is higher than the static line rating 100% of the time. It also shows high increase of DLR current than the actually loaded current or static rated current of conductor. From the visibility of study of using DLR, problem conjunction affect the performance of network reliability and sometimes reduce the lifetime of OTL or case OTL fail. The alternative using DLR to solve the problem of conjunction are to build new network or extended new OTL. This costs a lot of money when it's compared to using DLR equipment. Based on offer by Ambassador Company, the 10-kilometer line tower construction cost €17 million. When calculated distance from network 1 and 2, the cost of money €309.4 million, but when can use the DLR devices, we can relieve or solve conjunction by €1.85 million. Conclusion, due to high demand of electric power, conjunction could happen on overhead transmission line. Using the weather parameter in calculation dynamic line rating of OTL could help in increasing line capacity. The maximum percentage of calculation error of our DLR calculation program does not exceed 2%. The difference between installation of DLR device to solve the conjunction and extending new line is very large. Extending new OTL take more time and more money, but using DLR not need more money or more time. Sorry, friends. Thank you for attention.
Thank you, Mr. Jamil. We will go directly to the next technical paper. Will be the title Overcoming the Challenges of Sustainable Energy Integration. Will be presented by Mr. Tim Spearing from Lossy Electrical, with 30 years experience in automation system field. Please welcome with me, Mr. Tim.
Okay, good afternoon, Assalamu alaikum, and thank you for the introduction. Yes, I've 30 years experience. I'd like to say my company, Lucy Electric, has 207 years experience. That's how old they are. Started life making iron, moved into making street furniture, making low voltage distribution boards, moved into making medium voltage switchgear, and we've been supplying SEC for about 25, 30 years with medium voltage switchgear. So you see, we've started from one position and we moved to another, and we want to keep in the game with how the whole market's changing now. So I just want to share some work in the UK, research work, on how to get more out of the network, to increase the capacity on the network to accommodate more renewable generation, in particular at the lower voltages, sort of 33, 11 kV, where you've got some solars and small renewable energy resources. Just the button. Trying to find the button here. That's the one. Got it. I got it. Yeah, I got it. Yeah. Okay. Just a quick snapshot of some work that's used our equipment. Up in the Orkney Islands, it's sort of very, very north in Scotland. Through using some techniques, this technology, they've managed to save over 5,000 tonnes of CO2 emissions in 2 years, saved some connection costs of roughly $36 million. I've had to convert that, on an island of about 21,000 inhabitants. There's a lot more to it than that, obviously, but it's just to tell you how you can make some gains. All about displacing diesel gensets with wind farms and other forms of renewable generation. Point is, though, it's not that easy. For the embedded generation at the lower voltages, you tend to want to find the least cost connection, which isn't really where the generation is. There's always constraints on the network. So what we're going to talk about is how to increase the hosting capacity on these networks. I'll skip a few slides, really. This has been the theme of the conference so far this week, where the network's changing. We're now bidirectional flows of power, of currents, and the renewable sources are closer to the customer. Just to look at a snapshot of a utility in the UK, over the past 10 years, their networks have changed quite substantially. They used to design a network for the worst, the coldest winter condition. I suppose it would be the hottest summer condition. And since the introduction of having renewables on their networks, the spread of the generation has been up and down. So you can see from that indication there, it's quite diverse. You couldn't really plan from that. So there's a definite need for flexibility on the network. So what we wanted to do, some work in the UK, was actually to find other ways of increasing the flexibility on the distribution networks through smarter techniques, making optimal use of capacity, and which will also afford the use of non-network techniques such as demand response. I mean, traditionally, when we make connections with generation, it'll be set for the maximum capacity. Everything's based on restoration post-fault. So what we're now looking at is actually trying not to have to restore, but to prevent the situation happening in the first place by managing the amount of generation on the network. This can be done with operational tripping schemes, which are quite common. Two of these schemes that I want to look at now is one called timed connections, and the other one is constraint management. And it involves the operator being more of a system operator rather than a network provider. So you see a lot where for the distribution operators that they are now becoming distribution system operators rather than managing the network. What was happening at the transmission, balancing the generation, now happens at the lower voltages on the network. And it's more of balancing the demand and supply. If there's more demand, you may want to bring in some more supply, schedule it in and out, so you're performing what would have been the work at the transmission level. So this is really the crux of it. Normally, when we've installed embedded generation or that type of plant, we've really catered for the maximum hosting capacity. And that's had some problems because you haven't really then, it's been difficult to add more generation without having more cost. So what we've ended up with is we've not fully utilised the actual space in that capacity. What we've found is there's a lot of latent capacity in the network. And it's that latent capacity we want to try and utilise with using more forms of generation and bringing the generation in and out. So the two techniques I just want to mention in terms of constraint management, I mentioned earlier, is the time connections and there's a centralised active network management system. Time connections then, this is actually work done with UKPN, UK Power Network, so you manage London and two other networks. Essentially, it's a piece of electronics on the switchgear at the connection point of the embedded generation. They've set a profile, like an envelope, whereby the embedded generation has to work within. It's not very clear on this picture, but essentially you've got summer and winter settings throughout the day. So it starts in the morning and increases during the day and drops off in the evening, almost like an inverse of the duck curve that was mentioned earlier. And the utility expects their customer, which is the embedded generator, to fall within this envelope. If they don't, now the electronics at the switchgear is monitoring this power, and will, if the embedded generator falls outside of this envelope, they flag an alarm to the customer and to the SCADA system. It's also set such that the SCADA system can then trip the breaker that's connecting that network, or it can also trip automatically. Really depends on the connection agreement with that customer. Now this system actually helps avoid large investment in upstream connections. It's trying to provide more generation at more points without having to make any big investments. That's why it's constrained within this envelope. A much wider system is where there's a centralised decision making. So there's quite a few of these embedded generators or renewable energy sources on the network. As you can see here, just as an illustration on the left here, we have some non-firm generation, and further along the line there's some energy storage. This is just an illustration, this one is. What we have is all of this generation and storage is connected to the utility system via switchgear, and this is controlled via the RTU, via the utility SCADA system. Running in parallel to that is this active network management system that's managing the whole system. So it's doing what the previous slide did, but on a much wider basis. And it's also talking to the customer's control systems to sort of say, right, we're at a point now where you need to sort of ramp down your generation because the capacity of the network is getting a little bit full. So how this works roughly, this is a slide taken from a body in the UK called the Energy Networks Association, which is sort of a group of the distribution network operators. And this is sort of showing the generation or the output on the y-axis, timer on the x-axis. And the dotted blue line is the output if we didn't have this system running. And we want to keep really below the red line, because that's really the maximum the network can accommodate. So when the system's running, then it amends or reschedules generation. And that bit there, which is filled in, that's the additional capacity we're trying to find in the network. Going back to the previous slide, where there's this unused or rarely used capacity, we're trying to fill in the gaps through bringing generation in and out. So this means we can get more generation on the network. We're increasing the hosting capacity of the network without actually spending too much money on reinforcing the network. Obviously, it will change over time, but it's deferring it by somewhat. So that's roughly about it. Essentially, this form of integration of distributed energy resources is finding this extra value in the network. Is it the right solution? Time will tell, because you do need to have contractual arrangements with the customers, with the people providing the renewable energy resources. And for sure, a common theme throughout this conference, flexibility has to be in from the start. It's a core element to the design. Thank you very much.
Thank you, Mr. Tim. We will allow for one question, please, only. If not, we will move to the next technical paper, Introduction of auto recloser in distribution network to improve the KPIs, will be presented by Mr. Nasser Al-Hakami with 14 years experience on automation, substation automation system committee. He is the chairman of that substation automation system committee in National Grid. Please welcome with me Mr. Nasser Al-Hakami.
Assalamu alaikum. Good afternoon, everyone. Where is this slide? Most of us know Pareto, 20%, 80%. Financially, we don't like that, as 20 of rich people owning 80 of all of the money. But as an electrical engineers, we are doing that in the good manner. We are concentrating in the 20% of the weak point to enhance the system by the 80%. So our case study here, we are looking to the system that has a lot of failure, a lot of time of repairing, and then we try to look to the weak point to enhance it, even not to go to the 20%. We are looking to go by 10% to 90% of improvement. We'll go to introduction and objective, methodology, and then we'll go to the case study, and we'll conclude with some recommendation. Auto closure. First, we know that in distributions, in overhead distribution lines, majority of faults is around 60%. In some regions, increase from 7 to the 80% as a transient fault. But in the system, most of the configuration, they are using a fuse. And fuses need a time. Need time to find the location, need time to repair it. But with introducing the auto closures, we will try to solve that one, to enhance our system KPIs, to enhance the system reliability, and to reduce the losses as revenues for the company. Auto closure is common in transmission lines, but in distribution is not that much utilized. We will look to the SAFE and to the KD, to the SADI and the SAFE that we are looking to improve as the duration and at the frequent rate of the failure. This is some snapshot of the field installations, how it look like in the field. It is an outdoor auto closure system equipped with the protection systems. We have two objectives of auto closures. The common one is to increase the reliability. That's the most used in the transmission system. But in our case, we have another objective to enhance the KPIs of the system, the SAIDI and the SAFI. We'll go through the definition of the SAIDI and SAFI. SAIDI is the total durations of interruptions per customer among the all customers connected to the same grid. And the SAFI is the total number of the interruption. They are related to each other. As the number of the interruption increase, the duration increase. We are looking to use the failure mode effective analysis. It is a nice methodology that looking to the effect of a single failure to other equipment. So we are calculating the time if the failure occurred in my zone, also if the failure occurred in other zone affecting me, as the system is interconnected. So in our case study, we look deep. We have a system to the 100%. We go deeply to the 20%, and we go even to the 10%. So we selected the most affected and the most serious feeders, and then we go deep to the laterals and to see where is the most weak point. We are using the FMA, as we said before, to analyze the system, to enhance the SAIDI and the SAFI. There is a way, it's used by some utilities to select where is this 20% you need to improve. So we have a number of, as we can see, we have the number of the outage, and we are characterizing that one. We are scaling that. And we also are looking to the number of the customer connected to that feeder among the whole substations. And we are looking to how many laterals connected to that feeders. We are summing all the points, and we can find the best point that we need to improve. We selected here in our case study 33 kV with 14 kilowatt, and then the utilization at that one is 60% of the power. This is our feeders. It has 10 laterals connected to the feeders and 6 directly connected to the main feeder itself. We have 2 switches, and we have one switch at that lateral, the lateral number 8 down. It is only a switch, but doesn't have the capability of auto closures. So we analyze that one. We are creating a fault at each point, and then we are calculating how this customer affected by that load. We are calculating the effective SAIDI and SAFI for each load point, and then we are calculating the totals. So we are looking to the weakest point as the number of the user affected, and we are looking to the weakest point as it is increased the affecting to others. So we found that the optimal to use 3 autocrollers in these systems, 2 onto the main feeder and 1 onto the lateral down with the on-load switch, as it has more than 500 customers connected. As we can see here, this is the failure rate. We use this in the actual data, how the failure need from receiving the fault, moving the technicians, fixing, isolating, replacing the fuse. We calculate this time, we analyze all, and we found that each customer has a rate of around 7 faults a year and 9 hours out of service for that feeder, which is a high number. Conventionally, they are using a fuse with a low cost, but that doesn't work. So we installed the auto closures. We know that auto closure will reduce the failure rate. Consequently, the failure rate will reduce the time to repairs by 60% at least. So reducing the effect from each point to others will also give us additional reduction of 60, it will go to up to 70, 80%. So we make a 4 segment of the feeders by introducing the 2 auto closure on the main feeders and 1 auto closure in the lateral. And we found that a great reduction in the SAFI and SADI by around 70%. Even we reduce the failure by 60%, the SAFI decreased by 70%, the loss power reduction was 70% due to the interaction between the two load points. So we'll have small comparison between the before the auto closure and after auto closure. As you can see here, as SAFI is decreased from around 8 to around 2 point something, and the SADI also decreased with around 70%. At the end, we are looking to the money also. We increase the liability of the system, but the money is important for us as utilities. So the cost was around, by losing the electricity not supplied to the customer, around 26,000 a year for that feeders. With the, utilizing the auto closures, the loss reduced to around 7,000, and the net saving is 16,000 a year. 16,000, we save it a year, it will give a good return of money and return of the investment for the auto closure soon with the systems. In conclusion, control and protection can be improved using auto closures, but we have to be sure that the auto closure parameters, as it is reduced in terms of money, also is improve the stability of the system. We have some recommendations also will enhance the safety and the safety of the system and enhance the reliability of the system. We have to first to ensure the proper setting of the auto closure between the instantaneous and the time settings, how many shots we should set the auto closure in the distribution levels, that it will affect the customer equipment also. That need to be recalculated again for the system. The installation need to be accurate, to be tested in the professional way. We can also use a simple tool to identify the location of the fault in the laterals, as using sensor indicators. Also, we can use the sectionalizers with a time sequence with the auto closures. In advance, we can also use a distance relay to identify the location of the fault for fast response. And here is some snapshot of the fault locator. It's too simple, but it gives a great advantage of locate finder. So this is a tool. Thank you for listening. And at the end, I would like to thank my co-writers, especially one of my colleagues, our consultant in distributions. He supports us a lot, being in transmission. And also I would like to thank our Dr. Mohammed Al-Mihani and Dr. Mahmoud Gassas for supporting us. And thank you all for being patient.
Thank you, Engineer Nasser, a great case study. Again, to increase the resilience of the network, we need to review the control and protection settings with using the existing asset. Agreed with you that not only the autocloser, maybe the other equipment need to be reviewed in order to reach to the flexibility and the great resilience that we are looking for. Thank you again. Thank you. Engineer Nasser, if you have any questions, please, only one question, please.
Assalamu alaikum, Dr. Ahmed Abdul Wahab, King Abdulaziz University. I really enjoyed your presentation. Thank you so much for presenting it. My question goes to the using the auto closer. Have you tried the fuse saving mode instead of using the auto recloser, which will save the initial cost for installing these equipments, and it will result with a similar result in improving the SAVI and SADI. So I'm not sure if you tried that or not. Also, since you are trying to overcome counting the temporary outages, so probably you may want to include in your calculations the May fee, not just the SAVI and SADI, but also the May fee, which is also one of the KPIs used by ICRA in the KPI reporting scheme as well. So I may recommend using Maybe as well. In terms of the cost, you measured the cost saving. So I may recommend using the IEAR index, which is based on the reliability cost worth index that fits perfectly for your study. Thank you so much.
Thank you for the question. Actually, in our study, we concentrate on the implementation of auto closure. There is a lot of solution. There are a lot of solution to enhance the system. So our study, we are looking to the auto closure closely. For other indices, we already calculated. It's already in the paper. We calculated all loss of powers, non-availabilities, safeties, all the other factors included in the papers. So the 7 factors, the most 7 common KPIs for distributions included in the papers. This for your second question. And lastly,
cost saving.
Cost saving, we consider the installations, maintenance, the revenue of the powers. So that was included in the model of the system, cost saving. So starting by the installation, the maintenance, the return of the money, that also included in the paper. Thank you.
Thank you again, Engineer Nasser. We will go to the last technical paper will be presented by Mr. Ihtisham Al-Din Iftikhar Al-Din with 30 years experience in power system operations. He is working now in Transco. He will go to present last technical paper about BSS for controlling the system frequency and area control error through the AGC integration in Abu Dhabi Power Network. Please welcome Mr. Ihtisham Al-Din.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, Mr. Chairman. Being the last presenter of this session, I am feeling myself as a showstopper. But I believe that the show will not stop after me. It will keep continue, inshallah. But thank you, Mr. Chairman, for this honor. And I'm also thankful to all of the audience, the most passionate and most committed people still sitting and listening our presentations. This is a wonderful session. I really enjoy all the presentation, but specifically I want to point out 2 specific presentations delivered by my colleagues, Mr. Nador and Mr. Tim. Talking about the challenges specific to the higher penetration of renewables. And we all know that in the GCC countries, this is now the demand of the time, that we are investing heavily on the renewables. Now the both papers were talking about the challenges associated with the renewable penetration. My specific paper is basically providing a practical answer or practical solution that we have adopted in Abu Dhabi Transmission and Dispatch Company. So just to start my presentation and the content of it, that basically we are having a battery energy storage system already installed in our distribution level for the purpose of emergency support and for the peak shaving. Since the last year, we are having 1,000 megawatt, the world's largest solar PV on a single site plant in operation. And during the first year of operation, we have faced a lot of problems due to the intermittency of those PV plant. So that's why the TRASCO, the transmission dispatch operator, decided to take over the battery storage system and adopt a novel and innovative methodology to control the system frequency by the utilization of this battery storage system. And that initially saved us around 25 to 30 million dirham per year, just adopting the philosophy of utilization of this battery energy storage system. But before going to the depth of my paper, I just want to compare the two world largest battery energy storage system right now available and in operation in the world. The first one is the Hornsdale, Australia. I think many people are aware about the Tesla marketed. It's a world largest 100 megawatt battery system, single battery system. But we have another battery system installed and operational in Abu Dhabi. I'm just trying to compare both of them through the technology and the different aspects. In technology, the largest lithium-ion battery is sitting in the Hornsdale, Australia, whereas ours is the sodium-sulfur technology. In capacity-wise, 100 megawatt is the capacity of the Australian battery system, whereas in Abu Dhabi, the system is having 108 megawatt capacity. In terms of energy storage, the Australian batteries can supply 129 megawatt hour of energy, whereas in Abu Dhabi system, it is providing 648 megawatt of hour of energy, almost 6 times. And that transforms into the duration of support, 75 minutes in Australian battery system, and 360 minutes, that means 6 hours, continue at the rate of 108 megawatt per hour. The battery energy system of Abu Dhabi can provide full support. In this way, in this comparison, in all aspects, you can see that the energy storage system installed and operational at Abu Dhabi is to be considered as the world's largest single virtual battery plant. Now, how the reserves are reacting during an incident. The incident can happen in any shape. It may be due to tripping off any machine, it may be due to fluctuation in the load, or it may be due to the intermittency of the renewables, like PV. Once the cloud is coming, all PV start reducing their load, and once the cloud gone, PV comes back. And it creates an intermittency, or you can say the fluctuation in the controlling of the frequency. So let's talk about the reserves, how reserves came into action. System inertia is first line of defense. Power system operator knows the system inertia is the first line of defense. When the frequency fall happens, the frequency trapped by the system inertia. Then the primary response comes, it acts between 0 to 30 seconds of time and recover the frequency. And then the secondary frequency, which is start after the 30 seconds and will last up to 30 minutes, will kick in and control the frequency to the normal status. So these are the 3 types of reserve. But if I am keeping those reserves on my thermal units as a constraint, in the economic dispatch equation, it cost me a huge amount of money. So that's the challenge comes to us, another challenge, that how to optimize the usage of the battery energy storage system, and we start shifting those constraints from thermal units to the battery energy storage system. And it provides the relaxation on the thermal power plant and the better utilization of the fuel in a most economical way. And that's the reason we have saving around 25 to 30 million dirham per year. So how the battery energy storage system providing primary reserve or response? Usually this type of response, primary response, we are taking from the thermal power machines through the governor control, through the automatic governor control. And it is usually controlled through the droop setting of the governors. In the battery energy storage system, the response time is much, much faster because of the solid state technology. And it's similarly behave like a droop setting of the conventional power plant. These are some details, the work you can see in my paper. But for us right now, the most important thing is the secondary reserve, because the primary reserve is come into 0 to 30 seconds, and now because of the GCCIA interconnected network, our system is having high inertia, and the primary response is much faster and much, you can say the amount of primary response is much available to the system. But for me, as a Abu Dhabi system, the main problem is the secondary reserve or secondary control. So we start utilizing the battery energy storage system to overcome the forecast error, to take care of the interconnector deviations, and of course, the frequency control. For all these purposes, we are using a smart program, the package of our EMS applications that's called Automatic Generation Control, AGC. Conventionally, the AGC is controlling the output of thermal power machines. But here what we want to control the charge and discharge of battery energy storage system through the AGC signals. And it provides us an automatic response, secondary frequency response. This is the way the AGC program is calculating area control error, that it compares the actual frequency with the standard frequency and the tie line deviation, and after the performance of the calculation, it converts into an area control error. And this area control error becomes the trigger point for the AGC program to increase or decrease or allocate the increment and the decrement of the load to the thermal machines. I'm just, again, quoting a comparison and the example, the real-time example of the Hornsdale Australian battery power system performance. This is a 100 megawatt battery power system, as I told earlier. And you can see the blue and the red lines, these are the battery response for the frequency. So whenever area control errors require to increase the battery discharge, and whenever it requires to decrease the load, the battery starts charging. So it's basically taking load from the system. And these are the real-time example. The similar way, I have taken one example from my own system, that is the 7 October, 1,440 minutes throughout the day. And you can see these are the amount of area control error. That means these are the errors of my system throughout the day, every minute. We have put 25 megawatt as a dead band. That means if my error is 25 megawatt, no action is required, because 25 megawatt is within the dead band, so I do not want to disturb my machines to react to this small amount of error. But as soon as 25 megawatt dead band cross, I want to correct my area control error. And that is the time when my battery kicks in and provide me the response. Because right now I have only 108 megawatt battery installed, so you can see that on this graph there are some blue notches. Those are the notches where the area control error is more than 108 megawatt. It means whenever my area control error falls within the 108 megawatt margin, my battery provides quick response. And whenever it crosses that 108 megawatt, the remaining amount is transferred to my thermal machines. But you can see that throughout the day, most of the time, it's only battery who is providing me the reserve. And I am not disturbing my thermal generation. If you convert those into numbers, you can see that 933 minutes, which is around 65% of the time, no action is required, because my area control error is within the 25 megawatt dead band. Then 507 minutes, that is the 35% of the total time of a day, my battery is providing me the area control error response in both directions. That means only 16 minutes in a day, that is 0.07% of the time, I am disturbing my thermal units. So how it's transformed into the economics? It means that 99.03% of the time, my thermal plants are following my economic schedule, because I am not disturbing them at all, and they are following the economic dispatch schedule around 99% of the time in a whole day. because the disturbance are being taken care by the batteries. And that's the point where we have a huge saving in terms of economy and the fuel cost. So that's the conclusion, that the battery energy storage system is the solution, is the answer, one of the answer. Of course, there are many other answers available, but this is one of the answer to take care of the challenge of the intermittency of renewable penetration. It will provide fast frequency response, and it will provide a secondary frequency response as well when it is connected with the AGC program. Thank you very much.
Thank you, Mr. Hishamuddin. Of course, we will discuss more about your experience. And this is 180 megawatts. Is it old or new?
Actually, this 108 megawatt being installed by the distribution company in the chunks of 4 megawatt, 8 megawatt, and 12 megawatt in different locations. So that actually 10 locations, these small batteries were installed. The main purpose of the installation of these batteries is just to curtail the peak load of the transformer on distribution level. But now what we have done, that we have connected all those batteries through one SCADA system, and the entire battery storage, 108 megawatt, can be controlled as a single shot. So it means if I want a 30 megawatt increase, I will simply issue a command of 30 megawatt, and the program will decide and distribute among the battery storage, all the individual in battery storage.
Thank you, Mr. Hishamuddin. We pass our time for the session number 6. I think at the end we can say that we more resilience or more resilience or flexibility at the grid, of course, and no doubt that will support the more smarter, we can say, grid. Thank you a lot for our experts and our guests here. That's all. Thank you.
شكرا جزيلا للمهندس رائد الحارثي ولجميع المشاركين في هذه الجلسة. أدعو الآن الدكتور أحمد العبد الوهاب من جامعة الملك عبد العزيز لتكريم المشاركين في هذه الجلسة. مدير هذه الجلسة المهندس رائد الحارثي. المهندس مارك لاكروا. المهندس ألسان ندور. المهندس جميل محمد. المهندس تيم سبرينغ. المهندس ناصر حكمي. والمهندس احتشام الدين افتخار الدين. شكرا لدكتور أحمد العبد الوهاب وشكرا لجميع المشاركين في هذه الجلسة. والآن صورة جماعية مع المشاركين في الجلسة السادسة من المؤتمر السعودي التاسع للشبكات الذكية 2019. موعدنا يتجدد على رأس الساعة مع الجلسة الختامية لهذا اليوم تحت عنوان أمن وإدارة البيانات المتقدمة. كونوا على الموعد.
Ladies and gentlemen, we're having a coffee break for 30 minutes.
أعزائنا الحضور، أهلا وسهلا بكم إلى الجلسة الختامية للمؤتمر السعودي التاسع لشبكات الذكية. نتعرف في عجالة على أبرز المشاركين في جلسة أمن وإدارة البيانات المتقدمة.
Ladies and gentlemen, welcome to the 7th session titled Advanced Data Management and Security, chaired by Dr. Amr Al-Asad, Director, National Center for Telecom Systems, Command and Control Technology, King Abdullah City for Science and Technology. First paper, Cyber Physical Data Attacks, presented by Rafat Rob, Saudi Aramco. Second paper, Prediction of Electrical Peak Demand in Smart Buildings Using Time Series Analysis, presented by Muna Abdullah Al, Princess Noura bint Abdurrahman University. Third paper, NeumBot, an Edge Computing Communication Framework for Smarter Buildings, presented by Ala Badukhul, CAX. Fourth paper, Prevention of Non-Technical Losses in Pakistan Using Smart Meters, presented by Saifur Rahman, Superior University. Fifth paper, Importance of Smart Meters Data Processing, a case study of Saudi Arabia, presented by Abdullah Sbeir, CAPS.
رحبوا معي بالدكتور عمرو الأسعد وجميع المشاركين في هذه الجلسة.
Assalamu alaikum. So thank you. I would like to thank everyone here for being patient and stay with us for this last session of this conference. So today we have 5 speakers and we have time frame of 1 hour. So we'd like to ask the authors and presenters to provide the talk in 10 minutes and give us and leave 2 minutes for any questions. Entitled Protecting Power Systems from Coordinated and Dynamic Malicious Data Injection Cyber Attacks. So we have excellent speaker. We have Dr. Khalid Al-Ataibi. He's currently an Aramco employee working in Power Systems Cybersecurity team. He has a specialty in artificial intelligence, data forensic, threat analysis, and cybersecurity risk assessment. He had his master and PhD from North Carolina University in USA, specializing in machine learning and cybersecurity in years 2009-2016, respectively. So with that, I would like to all of you to welcome Dr. Khalid.
Good afternoon, ladies and gentlemen. I am Dr. Khalid Al-Ataibi. Today I will present our work with our team leading by Dr. Rafat Rob, entitled Protecting Power System from Coordinated and Dynamic Malicious Data Injection Cyber Attack. Basically, we are highlighting a specific scenario that targeting the data analog of the power system. This scenario are very sophisticated that can bypass all validation tests on a power system. The effort of this scenario strategy starting by the effort from North Carolina State University and North Carolina Chapel Hill by Dr. Leo and Michelle. Basically, this attack is trying to hide the data contaminations when it's received by the control center, where the attacker, he always look for the data attack very sophisticated and it has the same properties from the original data. As we know, in a power system, all the data are vectors data, and those data, each single vector has features. So the attacker always look at the plane where the data are spanned by looking for the subspaces and of these vectors. Always the attacker looking for non-zero attacking vector to contaminate the original data and send it to the control center, where the control center apply the validation test. The thing is, some scenarios can bypass the validation test in a control center where the attacker will be hidden. And in some publication, they called it hidden attack. If you look on the last equation, the attacker always his aim to take the validation test when he contaminate. If you look at the variable V's, which is the attacker vectors to contaminate the original data Z. When the attacker applied such a vector, sophisticated one always would give him before and after the attack the same values. And the C here is representing the estimated corrupted value that will be attached in the state variables of the Bower network. Here is the false data injection. Some effort of this work targeting the direct to the sensor when the attacker can have the capability to compromise the sensor, and some effort goes to the applications level. Our work, we prove it in a practical and in the mathematical concept. We target the automation software by assuming the cyber adversary agent was embedded in that software, but when all the data aggregated and the attacker could find out the configuration matrix of the Bower network and contaminate the data before it's attached to via the SCADA network to reach the control center. Here is the algorithm for the attacker for his agency, basically collecting all the data, create the topology matrix or configuration matrix, and try to copy all these matrices in the same plane to target the same spaces and subspaces. To create attacking vector that have the same features, basically trying to get the vectors from the mathematical concept that going in the same direction from the original data. So when the attacker create this thing and he check the null space of that matrices he created. If the matrices is a full rank, this is a mathematical theory, all the solution will be available for the attack, it will be 0, which means there is no solution for the attacker. But this is not the customized case in the power system. Always the null space for the copying vector is less than is not a full rank, where always there is non-zero attacking vector. If we look here in the yellow circuit is the attacking vector. Always it has to meet the conditions by multiplying the configuration matrix by the estimated corrupted value that will be in the state variables. We test the attacker approach in IEEE standards by taking a 9-bus system. We had 26 measurements and we have 16 state variables. When we apply the algorithm, as you see, the before and after the attack, if you look at the first column, you will see all the measurements that are available in this IEEE standard, and we have all the measurements, which is the analog data from the field under the Z value, and we estimated them. When we apply the validation detection test in the control center by taking the two norm and finding out the residual value between the measured value and the calculated value, we found it at a certain value. Then we apply the attacking procedures, and we create attacking vector that MV, and we add it to corrupt the original data of the system. Then we end up with the same values. Before and after the attack, we have the same value, which means the attacker, he could bypass the validation test. Why we called it coordinated attacking vector? Because the attacker always try to create the coordinated values with the original data. When we have a coordinated values, always it will result as a residual 0. Our proposed solution, just we take a look for the encryption method. Encryption method, basically, we have a text, a plain text, and we have a secret key that will known from the sender and receiver. This is the baseline for the encryption methods. When the text received by the receiver, he will apply the receiver the same private key to decrypt the text. The same method was applied, but we take in consideration the topology, which is the H matrices, the configuration matrix, from the attacker point of view. And if you remember with me the previous picture, we had IO concentrator. We applied our algorithm to create a spy node to mislead the attacker by making sure the attacker, he cannot understand what is the exact topology. So when he applies his algorithm, he will find only a zero factor where he cannot contaminate the data. Dr. Rob, he suggested, Dr. Rafat, he's the originated for this solution. He suggested we need to find a sophisticated algorithm to choose the location of the spy data. The spy data has to be very well calculated to make sure the system doesn't go unobservable from the attacker point of view. We all assume the attacker is always smart and he can understand the right data and incorrect data. We apply the spanning tree on the 9-bus system I presented in the beginning. And the spanning tree starts with the highest important nodes we have it in the network. Here, at the highest node, it depends on how many connections on that node. If we look at this 9-bus IEEE 9-bus system, we have 7, 9, 4 with a degree of 3. In this situation, we just take randomly one of them are the important. Randomly, we pick node number 7, and all the connected nodes to number 7 become observable as well. Now the nominations between the importance of among those nodes go between 2 and 5 and 8. We have 8 and 5 are the most important at this situation. Randomly, we pick 5.
Dr. Khalid, I kindly ask you to conclude in 2 minutes, please. Thank you.
Excuse me?
I kindly ask you to conclude in 2 minutes.
Okay. Just and the procedure will continue until we reach to this table where the correct and the perfect solution to place our spy data from the cyber attack point of view. The second step, from the attacker point of view, we need where should we place our spy data from the attacker point of view in the transmission line. We pick in the middle, and all the parameter has to be changed, and the calculated for the state estimator should go based on this from the attacker point of view. This is the end. Our algorithm, we do it as a firmware in the IO concentrator, where in the beginning, if you look, the rank of the matrices was 25, which is a not full rank, where the attacker, he has non-zero attacking factor, he can contaminate the data. The iteration goes for 1 month, one more time, and the rank, until the rank reached to 26, where the attacker, he has only one identical solution, zeros. If he used them, that means there is no contamination. If he put a random value, that it will be detected by the available validation test on the control center. Here, our simulation in the same IEEE 9-bus system. If you look, all the values or all the nodes highlighted in the blue is the data from the spy node, from the attacker point of view. And when he copy his matrices to create the non-zero attacking factor, he found only one solution as a 0 on the last column, where he cannot contaminate the data without being detected. This is the summary of our work. And always the attacker, he's really smart, and this is very sophisticated to create a specific factor for a specific power network. And also the assumption, the attacker, he has a well background in the math, so always we look to make the attacker have a full rank matrices, so he cannot contaminate the data, and he will have only one attacking factor, which is 0. Thank you so much. I will be more than happy to answer your questions.
Thank you very much, Dr. Khalid. It's fascinating work. It's unfortunate that we don't have enough time to get any questions but I would appreciate if the audience who is interested to ask questions to the author, please take that offline and ask them probably in the break time. So let's move on to the next talk. The next talk that we have is entitled Prediction of Electrical Peak Demand in Smart Buildings Using Time Series Analysis. We have excellent speaker. Our speaker is Dr. Munad Dailij. She is with Princess Noura bint Abdurrahman University in Saudi Arabia. She had her PhD from University of Western Michigan University, and also has a master from King Saud University. She has a great professional experience. She is now Vice Dean for Educational Affairs at College of Computer Science and Information in Princess Noura bint Abdurrahman University. She also taught a large number of courses and had many large experience in doing research. So without any further ado, please welcome with me Dr. Mona.
Assalamu alaikum. Bismillah. Today we are talking about prediction of electrical peak demand in smart buildings using time series analysis. Where is the pointer? Yeah, okay. Actually, nowadays, the energy consumption reduction is one of the most important problems. خليني أستخدم هذا أحسن. That affect people and government. Our aim is to reduce the electrical consumption within and maintain the same level of the user's comfort. So these two, we have to manage these two challenges in the same time. Intelligent building or smart building, as you know, it can be defined as a building that can maintain the same the grid power and maximize the service efficiency for the users. This building has special components like sensors, renewable energy source, and energy management system. Here, this is the most important, which is the energy management system. Our methodology in this work will be how to predict the occurrence of the peak load hours experienced by end user. As you know, we usually use the electricity or energy during the days, but there is certain hours that all of the people use this energy more than other hours. This hour is called peak. So in this work, we want to predict the peak for the next 24 or 48 hours so that each user can manage their usability of this energy. We will use 5 different models were applied on electrical consumption data of 5 government buildings at Cardiff, Wales, United Kingdom. Actually, the model comparison that we use depend on the accuracy of these models, and we choose the best one with the high accuracy. We will only talk the names of the models. If anyone wants more details, we can give them later. These models are 2 kinds of regression, multiple and dynamic regression, 2 kinds of time series, ARIMA, and another a modified version of exponential smoothing model, and the last one, which is kind of machine learning. As you know, it's ANN, the artificial neural network. This is the process of the data, how it's from the beginning until the end. Actually, each building nowadays have a building automation system. It can be any sensors or grid measures, so which take the data and store it in a database. Now we can take the data and transfer it in a good way, so we can analyze these data, then diagnose any noises that it can be and detect any anomalies in the data. Actually, the data then can be split into training data and test data. The training will be go through the predictive models, and as we said, we tried 5 models. After we choose the best model that we want, then we test the rest of the data to make sure that this model is working very well. Starting with data analysis, we have electrical consumption of 3 buildings. As an example, from 2014 to 2018, here the electrical consumption and during the times, and it it appear how the buildings are different wisely in the electrical consumption. If we go deep on the data, taking weekly consumption, we will see that the more consumption within the 5 days of the working days, which is from Monday to Friday, and on the weekends, which is Saturday and Sunday, there is less consumption. Going more deep, if we take the daily hours from 0 to 23, which is the hours of the day, we see that like a normal curve, the peak, as we talk about it, the peak hours, which is, we can see it here, it's in the middle, from like 10 to 12 or 1 o'clock, which is the high consumption of the electrical, and at the beginning and the end of the day, here are the less consumption. This is the plot of our raw data for the 5 days, and here the 5 predicted models. We got 4 of them predicting the data very well. And the last one, which is the regression with the purple line. Here the plot on the right, the ARIMA, which is the best one, have the good forecasting for the 6th day. As you see, the model performance was measured by mean absolute percentage error map, and the accuracy, it's from 74, which is for the multiple regression, until 99 for the time series model to the TBAT and ARIMA. As we said at the beginning, our focus on the peak. So when we compared the peak demand for the forecasting model, we see that as example, for the 3 buildings, that the peak hours is different, and some buildings have 1 peak and other have multiple peaks. And usually it's in the middle of the day. In conclusion, a peak energy forecasting framework for a group of buildings is presented. Actually, since we have only limited time of any information we need, you can ask about it. The decision support in building data can be developed in communities and cities level. The 3 predictive models are competitive with high accuracy model, and then the recommender system can be established based on the big intelligent forecasting model, which will suggest the correct consumption behaviors. Lastly, the future work is how to replicate this model on the data from Saudi Arabia. This is our goal. Number 2, develop a smartphone application to offer to end user a forecast of the day ahead, demand load to shift from the high loads to period where load is low. So as I use a Google map to know which the street is less traffic, I can use the smartphone to tell me which hours is low on the peak consumption, so which is accordingly, which is low price, so I can use the electricity on that time. Why Saudi Arabia is an ideal test bed for intelligent energy management? Actually, as we see these days that energy consumption has increased, including also the prices increases. The test bed for it's a best ideal place for integrating renewables, since we have a great power or solar production capability. So we hope that we can build a new models or the same models and apply it on the data from Saudi Arabia. I hope within the time. Okay. Thank you so much. And if you have any question, please don't hesitate.
Thank you very much, Dr. Mona. I think we have 1 minute for a question, quick question. If anyone from the audience has any question to the author. So I have maybe I can ask one question. So you said that in the future work you will be collecting data from Saudi Arabia in your training set. So
What's that?
in your future work, you mentioned that you will be collecting data from Saudi Arabia to apply to your model.
Yes.
So what's your plan? Were you able to get this data so far? And if you have any hiccups with that, so maybe we can share with the audience so that they can help
Thank you so much for the question. That's what I'm here. I'm here to manage contact with any people so they can get any data for buildings, for communities, for campuses. We are proposing a model for Princess Noura University to apply a pilot in some building to develop the same in a data. And I have a look on the exhibition and see how some companies have a smart grid, so we can apply it in campuses or everywhere. Okay?
Thank you, Dr. Mona. So our next talk is entitled An Edge Computing Communication Framework for Smarter Buildings. So the speaker is Engineer Ala Badukhun from King Abdulaziz City for Science and Technology. He's a great presenter and speaker. He had his master from Case Western Reserve University and bachelor from King Abdulaziz University. He had good number of applications and had excellent experience working in IoT, edge computing, embedded systems, etc. So without any further ado, please welcome Engineer Ala.
Assalamu alaikum. Good afternoon, everyone. Almost all the panelists here today or yesterday at the conference have at least hinted the idea of edge computing, hence showing its relevance and importance in the area of smart grid. And today I come here to share with you a communication framework project that we are actively working on, which inherently focuses on enabling node-level edge computing. Specifically, our topic for today is to illustrate how such a framework, or what we call it NeonBot, it can enable such a system. To begin, a little bit about NeonBot. The name comes from two abbreviations, the word Neon and bot. Neon stands for new future, obviously, and bot, which is a reference to a smart and autonomous piece of software. The project has initiated back in 2016 with the main objective of standardizing IoT communication framework, as well as having the ability intrinsically to process data locally on the edge. And about building management systems, it's a definition that encapsulates the idea of monitoring and controlling systems and appliances within a building, such as HVAC, lighting, access door, etc. And till recently, BACnet is becoming the mainstream communication protocol for this for BMS and building automation, with more than 1,000 compliant hardware vendor. However, BACnet is facing a threatening challenge, which is the interoperability. You see, though vendors are applying the same standard, it's not well identical between vendors. Each vendor applies their own custom object types and their own messaging between appliances. So this is a challenge in the spectrum of BACnet and building management system overall. NeonBot, on the other hand, is built to be workable and interoperable with all the things that have to interact with the internet or interact with end users, such as robotics, health monitoring systems, you name it. Also, as well as this centric idea, it focuses more on the ability to decentralize computing. Computing can be done on the edge fully, enabling features such as edge intelligence and AI on the edge. This is the main two centric points, as well as the ability to be geoscalable and adaptive, cost-effective, use different off-the-shelf components, as well as have the ability to perform upgrades and updates of the firmware on the air. You see, when you have millions and billions of nodes, you have to think of an intuitive way to perform updates and upgrades, as well as add-on features such as machine-to-machine security. So to illustrate further, I made a small, modest application of traditional BMS and against how the alternative would look like with NeonBot. And at first glance, you see the hierarchy of the backnet controller and routers compared with NeonBot. NeonBot is actually just the end edge node that connects directly to the sensor or the controlled item or component. Whereas to control a single item in backnet, you need more hardware. To dig deep further, we actually compared, we made a small comparison in that regard. We, in that particular application, we counted the number of needed hardware. And as you see here, NeonBot uses less hardware or components that need to work for only NeonBot compared with a conventional backnet system. And with regards to the power consumption, it's very noticeable to see that NeonBot can consume more than half of what backnet appliances or backnet components or hardware is consuming. Even though it's just a little bit, but when you have millions of appliances to be controlled, this will be very much considerable. And this is also a modest, you can say, cost of the comparison of the cost between conventional backnet, well-known backnet system, and off-the-shelf components of NeonBot. And at the end, we actually look for NeonBot to become a future for the Internet of Everything, from healthcare to mobile robotics, to the Industry 4.0 components and hardware, to even healthcare, CCTV, smart cities. All of these edge devices communicating with each other will actually have a very good impact in the ease of life and the way of the quality of life we are living, and much more space in innovation and integration. Hope I was a delight. Thank you for the time, and if you have any questions.
Thank you very much, Ala. So questions from the audience? Anything? Okay, so I have a question for you regarding this edge computing, which you... Okay. Yes, please. Go.
Okay. Well, thank you for your informative presentation. I have two questions. One, which protocol you are using for harmonization and synchronization between different devices, And the second, your Neom bot seems to be a very simple device. What about the cyber security? Someone can hack it, attack it, and then damage your system. The two things I want to know.
So I will answer the second question, then I will come to the first question. With regards to NeomBot, NeomBot is not a device, it's a framework. And the device, you can name the device as a NeomBot client. And the NeomBot client can be any platform, really. It can range from mobile phones to sophisticated single board computers, and can run also on different operating systems. This is in that regard. All the devices, one of the main goals in NeomBot is that all the clients use the same communication stack to communicate with each other. And relatively, we have tested this on two protocols. One is XMPP and the other is MQTT. And both achieve the same results. The main idea is that we achieve edge computing on the edge level, on the same node. And this is the main centric idea. Yeah. Any question? Doctor, you have any?
Just quick question here. So with the promises of the 5th generation of mobile communication, the 5G LTE, so because the promises there is to reduce the delay for edge computing. So what's the future of this work and the presence of this 5G networks?
This is a very relevant question. Though we will have, in the near future, we will have 5G, very, very high-speed networks, it's also relevant to note that the number of IoT devices in general is exponentially increasing. And at some point, we might not be able to cover everything. We might not be able to cover the huge amount of traffic of data. Just to give you a quick illustration, like in CCTV, for example, you need a very huge bandwidth to transmit CCTV streams. And that's where edge computing comes into play. You will analyze the image further, you will process it, you will do compression in order to achieve, it can operate in a low latency. Yeah.
Thank you very much. So please thank with me Ala for his presentation. So our next talk is entitled Prevention of Non-Technical Losses in Pakistan Using Smart Meters, Case Study of Pakistan. So the speaker is Dr. Saifur Rahman. He has working as an assistant professor in the Faculty of Engineering and Technology at Superior University, Lahore. He has also been a lecturer in Electrical Engineering Department in University of Lahore, Islamabad campus. He had PhD in Electronics Engineering from Capital University, Islamabad, and Master of Science from Muhammad Ali Jinnah University in Islamabad, Pakistan. So please welcome with me Dr. Saif.
Thank you, everyone. Good afternoon. I am Saifur Rahman from Pakistan, and I am here to present the paper on the behalf of Ms. Faiza, who could not come here due to some personal issues. So this is the topic of my paper, Prevention of Non-Technical Losses in Pakistan Using Smart Meters. Here is the abstract of my presentation. As you know, energy crises are increasing day by day all over the world, especially underdeveloped country like Pakistan. We are facing huge problems. The utility companies of Pakistan are facing big problems due to these losses in electricity in the form of financial problems, technical losses and non-technical losses. There are two main concerns in this topic. Technical losses can be found out by using some geometrical and some specific methods, some equations that can be handled. But the main concern is this advanced metering infrastructure is used for non-technical losses. So in this research, smart meter-based simulation solutions has been presented. Technical losses, as I have mentioned earlier, the dissipation of energy in the components of transmission line, that is in conductor, transformers, and the magnetic losses in it considered as technical losses. The distribution line losses in which energy is dissipated as heat also comes in the category of technical losses, and that can be calculated by using some design and construction phase. Non-technical losses that can be occurs because of fraudulent activities. Electricity provider face big revenue fatalities due to these losses, and these losses are the three types of. First one is meter altering, that can be used by some magnet, some non-payment of bill, also by direct hooking, that is known as Kunda system. Unauthorized connections are also, I have described. That is the challenges in Pakistan, as Pakistan has mechanicals meter, and that is based on manual system, due to which risk of electricity theft and meter tampering is very high. And there is a need to change this old infrastructure into some systematic way, so that this problem can be handled. And according to the survey that can I present in this presentation, 58% of the bills of SEPCO, that is Sakhar Electric Power Company, that have based on real data, have been paid during the year 2014 and 15, 58% revenue that we have lost. This is losses per year due to some different theft techniques. That is by passing meter connection, it is almost losses per year, 0.0960 millions per year. And second one is the direct hooking, that is the losses 0.169855 per year. Reverse meter counter, similarly use of magnets, directional changes, wires stamping, and the total losses per year in millions is 0.781822. This is the billing rate in SEPCO due to theft issues, 2010 to 2011. We have billing 24020 res, and the payment that we have received 11782, and the percentage is almost 49%. Similarly, 2011, 2012, 2013, and in 2013 to 2014, we have 59% of the issue we have in theft billing rates. This is the data based on some realistic line losses in feeders of Lahore, Pakistan. We have collected this: Allama Iqbal Road, Babdar House, Nicholson, Davis Road, Alhambra, Governor House, LDA, and Ahmednagar. The receiving units and the sold unit. And you can see there is a big difference between received units and sold units. The losses per year cost almost 12.6, 1.8, 15.4, 10.2, and so on. This is the overall data of Pakistan of different electricity power supply companies. We have LESCO, Lahore Electric Power Corporation, FESCO, JESCO, Gujranwala, Multan, MEPCO, Islamabad, Hyderabad, and here is we have energy losses in billions rupees, 2.35 billion in LESCO, 0.6 in Faisalabad, and overall 75.89 billion we have the energy losses in rupees. So in order to avoid this theft problem, in this paper we have introduced an algorithm that is a proposed method. We have a smart meter that collects the data and send it to the external data control system. Again, in flowchart we have a generator that is has been deployed in generators harmonics, and it generates harmonics, and if technical losses exceed 3%, then cut, otherwise it's operate in normal operation. Then operate the harmonic generator, disable harmonic generator, and reconnect genuine customer. During this period, we can operate the proposed theft problem. This is again the flow chart of my proposed work. So, proposed model of smart meter system and theft detection. The external control station computes non-technical problems and can control if it is greater than 3%, then it cut off the supply to the legal customer. Meanwhile, the harmonic generator will generate the harmonics and which will affect the appliances of non-genuine customer. After this process, the EC will generate a signal for ICS to restore the supply for genuine customer. This is the conclusion. Direct hooking and other theft problems can be resolved by using this method. Although our proposed method is costly, but it appliances for non-genuine customer and will damage, but theft rate can be reduced very significantly. And overall energy can be saved by providing to genuine customers. Thank you. These are the references.
Thank you very much. Questions from the audience? No questions?
Assalamu alaikum. Diab Al-Sinani, the University of Sydney. I just have one quick question. Is this method even legal? The proposed method, is it legal? I mean, you are punishing the customer before taking any legal actions or making sure that they are really maybe taking the power in an illegal way. So you are taking a right action and destroying their appliances before taking any legal actions.
For a genuine customer, then it will apply again, and our genuine customer will not be affected furthermore.
Okay.
So got it?
I'm sorry, I couldn't hear you.
I am saying that the proposed method, when we apply this, it will affect the genuine customer for only 3 to a few seconds. Then the harmonics will generate and it will destroy the other signal, so that in this process we can save the energy, and it almost take a few seconds.
Okay. I do think there are some legal aspects of this problem, actually, or this proposal. Thank you.
Thank you.
Thank you very much. So our last but not the least talk is entitled Importance of Smart Meter Data Processing. It's a case study of Saudi Arabia. The presenter is Dr. Abdullah Sibai. He is with King Abdulaziz City for Science and Technology. He received his PhD and master from University of British Columbia in Canada, and his bachelor degree from KFUPM, Saudi Arabia. He has been working in joint research projects with the Saudi Electricity Company, and they have made a great success. So today, I think Dr. Abdullah will shed light on one of these projects. So with that, without any further ado, please welcome Dr. Abdullah Sibai.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon, ladies and gentlemen. Thank you, Dr. Amr. I appreciate the introduction.
In this presentation, I will be presenting a result of a project that is part of the CACST SEC Joint Research and Development Center for the Distribution Sector. I would like to acknowledge my team, Dr. Tamer Ghami and Murad Anwar, and also the team in the center who contributed to different ways to that project. In this project, we were looking at the smart meter data and trying to develop a demonstration system for improving the quality of the data. There is a background to that. As you know, Saudi Electricity Company is launching a major smart meters program. We are expecting more than 10 million smart meters, and as we grow in number of users, we'll have more and more of those meters. The SEC has launched several demonstration projects in different locations to look at the different aspects of the smart meters or the advanced metering infrastructure. It's not only SEC, also when we talk about the smart meters programs, the National Water Company also has its own smart meters program, and they expect to have more than 2 million smart meters by next year. So we are expecting a large amount of data coming into our national utility systems. So what can smart meters data? Smart meters data can provide utilities lots of opportunities. In this session only we looked at two applications. We looked at the energy prediction in the buildings. We looked at prevention of losses, either technical or non-technical. Also, you can automate the billing system. You can have a better understanding of customer segmentations, and you can zoom in the customer's load profiles, which will give you more insights, and it will enable the dynamic pricing strategies. So smart meters data analytics, which are the tools and the application that will enable you to utilize the smart meters data, is becoming an active area of research, and I'm sure we have seen some of them in this conference. However, to be able to have the above benefits and utilize the smart meter data, you need to have a good data, which is healthy, clean, and ready to be used. There are lots of issues with the smart meter data that is coming from the actual implementation of the system. Sometimes you'll have missing data points in your packets. Sometimes you have duplicates, zeros, outliers, and format mismatch in your systems. Not only that, which makes the problem more complex, is that utilities tend to have different vendors, so they bring into their network different smart meters from different manufacturers, and that makes the problem complex. The demonstration projects have shown the need for smart meter data processing. Typically, as we see, if we go into the academic and the literature, you will see in every application when they develop their algorithm, they add a component within the algorithm to deal with the data quality. In Dr. Zumana, there was a noise treatment in the algorithm, which handles some of the issues in the data. The approach we are talking about here is quite different. So the SEC launched several demonstration projects, and they tackled in one of the projects, they looked at the smart meters themselves. In some other projects, they were looking at the communication technologies. Some other projects looking at what can be used for out of the smart meters, and the MDM, the meters data management. So the data quality issues was highlighted. So there was a need for a pilot system to deal with the quality of smart meters. And the requirement is that we have a simple and easy to implement and a robust system for that. So there was this proposal, which was to have a framework for the data cleanup. And as we can see, you will have the smart meters bring the data to the system. And then depending on the specific format, you will have a converter where you will gather, identify, structure the data, and then using different algorithm for the cleaning and filtering with the visualization, validation, and then you store it in a unified data warehouse. After that, your data is ready for your applications. So in details, you'll first, you start with bringing the data, identifying its requirements as in the start. I will talk about the input data that we used for this project. When you read it, you need to have it in a unified data format. Each manufacturer has its own data format, and we built converter for the most commonly used smart meters manufacturers in SEC network. However, in the algorithm, if the data format that is coming does not belong to one of those converter, the algorithm will generate an automatic converter for that. After the conversion of the data to the unified format, then you deal, this is the snapshot of the unified format. After dealing with the format, making it all uniform, then you will handle the issues with the data. And we looked at some specific data problems, either the missing, where you, the most commonly missing component is the timestamp of the data, and the duplicates as well, and there are details on the algorithm that are used for handling the duplicates and the outliers. And after that, you will have what we claim as a clean data that is ready for the application. These are snapshots of some of the statistical techniques used for the data implementations. And then after the data is validated, it is stored in a database that will make it ready in a data warehouse structure to be utilized for the applications. In this project, we gather a sample of 10,000 smart meters data as an evidence, a first insight on the quality issue, the usable data that are at least ready for the framework were over 4,000 smart meters data. So we developed a system with a graphical user interface for this demonstration projects, and we added several attributes to that where it can be located and utilize the data. Examples of the trials of this project is to have the energy density charts, and you can see the difference between just processing the data before and after. The smart meter count, which indicates how many smart meters are active in your network. It's an important piece of information for the utility and for the advanced metering infrastructure. You can see the results, how are they different between before and after the processing. The future work is that we work now, after we deal with the quality issues, we work on the applications. Some of them are the visualization, customer behavior, asset management, and short-term load forecasting. I will just shed the light on one of them, which is the customer behavior. As you know, there is the network load profile, and there is the customer load profile. And they should, or typically, they are not completely matched, as you can see from the two examples here. Not only that, even for the same user, they can generate different profiles in every day, depending on if it is a weekday or a weekend. So this is just an example of one of the applications that requires a clean and processed data in order to utilize the insights of that project. With that, I conclude my presentation, and thank you.
Thank you very much, Dr. Abdullah. By the way, Dr. Abdullah and his research team, they have a booth here where they showcase their excellent work. So I invite audience who are interested to visit that booth. So any questions to Dr. Abdullah before we conclude this session? There is one question.
Yeah, there is one there.
السلام عليكم. يعطيك العافية دكتور عبد الله. راشد from Aramco. Just regards about recording, is it just steady state or how about the fault scenario?
Can you clarify more?
I'm talking about cleaning the data. Is it just considered the steady state time domain? How about the harmonics, transient?
Well, the quality treatment, when you deal, it doesn't matter which data you are processing. However, you need to customize your algorithm in order to deal with the data. With the smart meters, typically what you gather from the customers, you gather the usage. That's mainly the usage information, the basic data, the billing data. These are the major items. Typically, utilities don't gather the harmonics data at that level. However, you can also create a framework for dealing with the harmonics. In theory, it shouldn't be a different.
Thank you.
Thank you very much. So now we are about to conclude this session. So I'd like to once again thank the authors and presenters and also the audience. Okay, so I think next is the Best Paper Awards. So
شكرا دكتور عمر. تبقى لنا شيء واحد، تفضل لو سمحت. تكريم الآن المشاركين في هذه الجلسة، وأدعو الدكتور فهد الصخيري عضو اللجنة العلمية للمؤتمر إلى تكريم المشاركين في هذه الجلسة. بداية بالدكتور عمرو الأسعد. الدكتور خالد العتيبي. الدكتورة منى الدعيلج. المهندس علاء بادخن. الدكتور سيف الرحمن. والمهندس عبد الله سبيعي. شكرا للدكتور فهد الصخيري ولجميع المشاركين في هذه الجلسة. أعزائنا الحضور، السيدات والسادة، ضمن مبادرات المؤتمر في مجال تمكين المرأة في مجالات الطاقة والصناعة والتقنية، يسرنا أن ندعوكم بعد قليل لزيارة الجناح المخصص لنماذج مشاريع الطالبات المبتكرة المنخرطات في مجالات الهندسة والطاقة في صالة العرض المقابلة وبالقرب من الملصقات العلمية. تلك المشاريع التي يمكنكم الاطلاع عليها ودعمها بالتأكيد هي لطالبات من جامعة عفت وجامعة الملك عبد العزيز. السيدات والسادة، وصلنا الآن إلى ختام جلسات المؤتمر. تبقى لنا التذكير بأبرز التوصيات التي خرجت من هذا المؤتمر، وهنا أدعو رئيس اللجنة المنظمة للمؤتمر المهندس بندر علاف لتلاوة البيان الختامي للمؤتمر السعودي التاسع للشبكات الذكية 2019 وإعلان الفائزين بجائزة أفضل ورقة عمل وملصقات علمية خلال المؤتمر. رحبوا معي بالمهندس بندر علاف.
السلام عليكم ورحمة الله وبركاته. حياكم الله في جلستنا الختامية للمؤتمر السعودي التاسع للشبكات الذكية. نشكر لكم جميعاً حضوركم لفعاليات المؤتمر والمعرض المصاحب، مشاركتكم في زيارة جناح الملصقات العلمية، حضوركم لورش العمل. بكل تأكيد نشكر الحضور من خارج المملكة لكل من تعبد عناء السفر وحضر لمؤتمرنا هذا. أدعو قبل تلاوة التوصيات الختامية أعضاء اللجنة العلمية المتواجدين في القاعة لتشريفنا بالطلوع على المنصة. تفضلوا. التوصيات الختامية. أولاً، تجهيز البنى التحتية المادية والتنظيمية اللازمة لدعم الاستخدام والانتشار الواسع للسيارات الكهربائية، مثل محطات الشحن الكهربائي العاملة بالطاقة الشمسية ورخص مزودي الخدمة. ثانياً، زيادة الاستثمارات في توطين معدات نقل وتوزيع الكهرباء والشبكات الذكية والعدادات الذكية. ثالثاً، دراسة الجدوى الاقتصادية للنظم الهجينة المكونة من الطاقة الشمسية والطاقة المولدة بالغاز والمدعومة بأنظمة تخزين الطاقة ودراسة تطبيقاتها في المناطق المعزولة. تسريع المبادرات الرامية لتفعيل مبدأ الوصول المفتوح للشبكات الكهربائية بهدف دعم نمو سوق تنافسي للكهرباء. الاستفادة من التطبيقات المتنوعة للشبكات الذكية، المباني الذكية، البيانات الضخمة، وإنترنت الأشياء للتنبؤ الدقيق بطلب الذروة. تجهيز خارطة طريق وطنية للوصول إلى اقتصاد الكربون الدائري عبر دعم التعاون بين القطاعين العام والخاص. انتهى. Now, this is the time to mention the awards for the best paper presented during the 2 days of the conference. طبعاً للتنويه، كثير من أوراق وصلت للمؤتمر، أوراق متميزة، والمحتوى العلمي لها رائع، ولكن جرت العادة أن يتم اختيار 3 أوراق لتكريمها خلال الجلسة الختامية. الورقة الأولى المهندس أحمد عبد العظيم من فرناس شومان لورقته العلمية بعنوان Placement of Electric Vehicle Charging Station in Metropolitan Areas Using an Agent-Based Network Graph Method. فليتفضل مشكوراً. الورقة الثانية Alisan Nadur from Saudi Aramco for his paper titled The Future of Saudi Arabia Grid, Exploring Large-Scale Renewable Integration Scenarios. الورقة الثالثة دكتور عبد الله السبيعي from مدينة الملك عبد العزيز للعلوم والتقنية عن ورقته Importance of Smart Meters Data Processing Case of KSA، فليتفضل مشكورا. زخم كبير وملصقات علمية متميزة وصلت للجنة العلمية للمؤتمر، وبناء على ما تم تقديمه وعلى ترشيحات اللجنة العلمية فقد تم الاتفاق على الملصقات التالية. الملصق الأول control. Distribution network reinforcement reliability cost worth analysis using generalized analytical approach. Nawaf Al-Arawi from Saudi Aramco. الملصق العلمي الثاني Leon Battery's State of Health Assessment based on Event-Driven Processing and Analysis by سعيد قيصر ومرام القثامي من جامعة عفت. الملصق الثالث A simple scale model for an on-road wireless power charging. حسن أبو ساق، مناع أبو ساق، سلمان الدوسري وأحمد الزهراني من جامعة نجران.
أبارك لجميع الفائزين في ختام هذا المؤتمر. هذا المؤتمر لم يكن لينجح دون دعمكم وجهودكم وحضوركم الفعال. أدعو جميع من في هذه القاعة إلى الصعود إلى المنصة لالتقاط صورة تذكارية. أهلا بكم جميعا. جميع من في القاعة بدون استثناء، هناك مساحة كافية كما في قلوبنا لكم. أهلا بكم. شكرا لكم جميعا السيدات والسادة. وهنا نعلن ختام المؤتمر السعودي التاسع للشبكات الذكية 2019، ونلقاكم بعون الله في 2020. شكرا لكم.